feel to it.
Yeah, it's got an almost improvisational tone.
This semester on Stat 201, prepare yourself for YouTube, because we're all zoomed out. Kahoots and special guests, Tiny Brian, Puppet Shark, Evil Moobot,
I am Moobot.
Morty the Rabbit, and more. Super Statistics Bros.
Hey everybody, we're live right now a little bit before the Kahoot. Kahoot doesn't start for an hour, but I was like, why don't we put some concepts in this video and get practicing the material? So I've already got some notes here ready to go. Let's do this. Put a note here that this is going to be the theory. So let's do this. So you're trying to understand what a confidence interval for the true proportion is. Well, first, let's talk about it theoretically and what you're trying to find. Probably one of the best ways to think about this is to think about when we would use it. We use this to find an estimate of the true proportion. So what does that mean? Bradley, good to see you there. This is totally real, and this is live. If you're watching this later, if we've clipped this, check out Stat201 Live when we're live for office hours. We're here to help out and learn statistics, and this is what this video is for right now. So when would we use a confidence interval to estimate the true proportion? Good to see you, Peyton. We'd use a confidence interval to estimate the true proportion when the question is categorical. The question we ask is categorical. So these are all like key facts right here. Fun facts about confidence intervals for the true proportion. So you need to make sure your question is categorical that you're asking. What does that mean? A lot of times it means the question can be like a yes/no question. It could be like, I don't know, do you like or not like this? So we can find out the proportion of people who like it. It can often be broken down as yes, no. And there can be multiple proportions, like the proportion of freshmen. So there can be more groups. So you could do like freshman, sophomore, junior, and senior, things like this right here, the proportion of juniors at the University of Tennessee. But notice how it's categorical in nature, and a lot of times it might be broken into a yes, no. I think one of the easiest ways to think about this is with an example. We'll be doing some example problems here coming up next. But when you think about the possible examples of this, it's going to be like estimating the true proportion of people who will vote for someone in the election. So when we do an election, it's do you support the candidate, yes or no? And good to see there, Maddie. Then we have a categorical question. And from that categorical question, we can derive an estimate of the true proportion of people who will vote for that candidate. So now that we understand when to use it, good to see Abigail, let's think about the notation for this. So we're just going to do some bullet points. We need to know the notation. If you want to chime in with some notation in the chat, that's awesome. I am still watching the chat as always, and Mubot is here, as you can see. So with this, notation for this is as follows. The first notation we have is p hat, and I have to do an insert on this. I have to go to here, insert equation. So we go to insert equation, and then we have to do the accent on it for p hat. We're going for very nice and beautifully written things. P hat is the sample proportion. Now, what can we find from p hat very easily? What is easy to find? Q hat. Complement of sample proportion. And Q hat is 1 minus P hat. We're going to do examples of this coming up, but you need to know the notation, you need to know how to solve it. And P hat is found by X over N equals P hat. And I guess we need to tell you what X and N are, right? How many votes does XYZ have? Are the questions phrased pretty obviously? Kind of. I mean, so yeah, it's like, we'll do some example questions coming up here. Yeah, it's like, are people gonna vote for Brian in the next election? And so you'd have the people who would say yes, and the people who say no, and then we estimate the true proportion of people who will vote for Brian. So we could do that. We could do that sort of example. And we're almost done with the notation on this, because now we have X is, and technically I think it's lowercase x technically, the number of successes, and then N is the sample size Oh, we can do that next coming up here. No, good, great stuff. Keep asking those questions. We do some p-value stuff and the conclusions. We could do the test for this coming up next. So the sample size is right here. All of this notation, you need to make sure you know it. And last but not least, who knows in the chat? Let's throw some points out here. Who knows what is the one thing we're missing for a confidence interval? If you know the equation, you know it. We're going to do examples coming up next, but we need the theory behind this. So what is the one thing we're missing for a confidence interval, which denotes the level of confidence or is related to it? So we're going to go over the confidence level related to Z star for this interval. So for this interval, we are going to use Z star, which is related to the Z-score for level of confidence. And to just briefly speak on that, please ask questions if you have them too, but what we need right here is if we're making a 68% confidence interval, we use a Z very close to 1, because that's the middle 68 according to the empirical rule. If we're making a 95, the Z-score is technically 1.96, which you'll notice is very close to 2. And that's a 95% confidence interval because it covers the middle 95. Notice as we get more confident, the Z-score gets larger, such that things like a 99.7% confidence interval is very close to a Z-score of 3. So a Z-score equal to 3 would cover the middle 99.7% of the curve. So the more you go out, 68 is 1, 95 is basically 2, 99.7 is 3. And we do use applets to get these exact numbers in our class. There are classic numbers. I'll write them here and then I'll erase them. But if you're wondering, 68 is basically a z-score of 1. 80 is a z-score of 1.2816, I believe. I might get the last decimal wrong from memory. 90 is 1.6449 or 1.645, a lot of people say. And 95 is 1.96, classic number in statistics. 98 is 2.3263, and 99 is 2.5758. The key to notice right here is that as you get more confident, you'd cover more of the middle of the curve, and the z-score, which are these things right here, goes out further on the curve. It has to get wider and wider and wider. Exactly. This is the empirical rule. Same thing. So it's the same similar idea for the empirical rule that finds the z-score for the percent of curve covered. Does that make sense, Briley? You are completely right that this is almost a review of chapter 5 for our class of the empirical rule. So the more confident you are, the bigger the z-score, which is related to how confident you are and also can be derived from the empirical rule of the 68, 95, 99.7. But we do more exact decimals because now 95 is 1.96 as the exact decimal. So this has been the theory part of this video. I might cut these up if you can't tell. This is going to be cut up in the video now. I'm not going to edit them. Sorry for anyone watching this in the future. Now we're actually going to do some problems. So my goal right now is to do a theory section and problems. What do people think of this in the chat? So we're going to do theory for each thing. I'm going to tell you the theory, like the most important things, and then we're going to do problems with it. So now we're going to do probably about 10 minutes-ish on problems, just doing confidence intervals, and we're going to switch to Charlie's topic. So 11:33, this is confidence intervals for the true proportion problems. So let's try to come up with 4 problems. And I'd love it if you put practice problems. I'd love it if you put some practice problems in the chat too. Because think about it. We can do true, false. We could do categorical or multiple choice. We could do fill in the blank. And we could do numeric solve. Okay, so true, false. See if you can come up with some. Or ask Mubot. Mubot might come. See if I can solve Mubot questions. Mubot's got the Mubot chat if you didn't know. But let's do a true, false. The only way to make a confidence interval more precise is to change the sample size. A confidence interval that is a 90% interval will be wider than a 80% interval. Wider. When doing a confidence interval for the true proportion, the third condition is nearly normal. Oh, we'll see. Let's do 3. That's easy enough. Okay. So as I'm doing this, there might be something that we didn't mention, and we need to review it. So the only way to make a confidence interval more precise is to change the sample size. The answer is no. This is false. Because if you look at the formula, it is p hat plus or minus z star p hat q hat over n. Everything after the plus or minus is called the what on this interval? Everything after, I'm looking for 2 letters in the chat. Everything after the plus or minus is called the what? Everything after the plus or minus. You see the plus or minus, you think everything after that is the what? Margin of error, exactly. Great job, John, right there. And then the first part is called the estimate. We're going to do some full work problems at the very end of this. This is the estimate of it. And what is it trying to estimate? Does anyone know one letter of what we're trying to estimate? The sample proportion is trying to estimate what, and you can see it in our notes. The answer is at the top. The whole point of this, I mean, I wrote it. What is it trying to estimate? The sample proportion, because we go out and we poll people, we're trying to estimate the true proportion exactly, which is P. So it's P hat is an estimate of P. So that's what we're trying to estimate. We're trying to estimate P from P hat. And we have right here the confidence level related to Z. We'll work one of those. But you can see that the only way to make a confidence interval more precise is to change the sample size. Precise means tighter. If you increase sample size, the interval becomes more precise. But if you decrease, it would become more precise too. Decrease the Z-score. So this would change precision, as in make it more precise. Intervals are more precise when you increase sample size or make them less confident. That's just a fact right there. And you can see it mathematically because n is in the denominator of the equation and the z is multiplied by the margin of error, or the standard error, excuse me, to make the margin of error. So the z is multiplied by what is called the standard error over here. So this quantity on the right is called the standard error. That is the standard error, which is a portion of the margin of error. A confidence interval that is 90% will always be wider than 80%. Well, what do you do with your hands when you say 80%? Here's I'm at 90. If I say 80, my hands are going to do what? We could look it up. We could find that, Bradley. We'll find that out. Or someone will post it. We'll find out for you. What do? I go and do what? If I say I'm going to shrink in, right? So 80, 90, or 90, 80. So an 80% is less precise and also less confident. Does that make sense? So when you go from 90 to 80, you're more precise, but you're also less confident. So a confidence interval that is 90% will always be wider. That is true. No, it's not a trick question. It's like, well, what if you construct it from different data? It should be the same data. It's not a trick question. Not meant to be. Don't outthink a question. When doing a confidence interval for the true proportion, the third condition is nearly normal. Well, what are our 3 conditions? The 3 conditions for the confidence interval for the true proportion are what? What are the 3 conditions? Condition 1. Random. Never overthink these things. Conditional. Random. Did we randomly select our data? So we need to have a random selection of data. Condition 2, less than 10%. And I say it this way because the way we do our conditions in this class, it's always the same 2 first conditions. I could go into great detail about the less than 10% conditions. If you're wondering, it deals with finite populations that can be oversampled, and then there has to be a correction statistically, which you'll have to use a different equation for. Don't worry about it too much because we don't test that big of detail on it. The check is, did we sample less than 10% of the population? So that is the simple check right there. And the last condition is what? Who knows? I know someone knows that last condition. The last condition for the testing or confidence intervals for proportions is what? The last condition. The last condition when testing, and we can do some practice problems here too. I now have a true false for this. It is success, failure. Great job. Success, failure. So do we have at least 10 successes and at least 10 failures? We're going to show this mathematically here in a moment. For categorical data, just simple categorical, do we have at least 10 successes, at least 10 failures? So let's go here to let's do one more true false. You ready? We take a sample of 500 students, and from this sample, there are, let's say, 15 who live in New York, do we pass the success/failure condition? Do we pass it, yes or no? We take a sample of 500 students. Do we pass the success-failure condition? You have to have at least 10 successes, at least 10 failures. So the way to do this is, how many successes, how many failures did we have at least 10? So what do we have? The question, this one's easy right now. I'll make it a little bit tougher in a moment. But we take a sample of 500 students and 15 are from New York. So how many successes did we have? How many failures did we have? The answer is yes, we do pass. So I will mark that right here. The answer is yes, we do pass. Well, the question makes it clear how many successes there are. There's how many successes. How many successes are there? That one's easy. 15 successes, and then the rest are failures out of the 500, 485 failures. So we do pass. So you pass because there's at least 10 successes, at least 10 failures. Great job, Daniel and Abby and John right there. How about this? How about now do we pass the success failure condition? There's 1% who are from New York. Do we pass it, yes or no, and why? So now you actually have to do the equation, which is NP hat. NP hat. The equation is NP hat. We don't. You are correct. So NP hat right here. And we also need that to be greater than or equal to 10. As long as it's greater than. Don't worry if it's equal to. And you are right. People are already figuring out how many successes and how many failures. And we need NQ hat to be greater than or equal to 10. And this right here, this one will be, because NQ hat is equal to 0.500 times 0.99 equals to 495. And then you can see this one right here is 500 is the sample size times the percent, which is 1, is equal to 5. And so now we do not pass. We only have 5 successes. So you need to identify your notation sometimes to make sure you can figure out if we pass the success failure condition, which we would not pass it in this instance. That's a really good test right there. We'll go and we'll do like a full interval here. Let's do a full question with this. And then we're going to do the next topic, which is going to be p-values. This is going to have numeric solve and a bunch of things. Okay, so Brian goes out and asks students if they have tried the new Taco Bell. Check it out on the strip. Baja Blast, everyone. So from his sample of 200 students, 200 random students, he wants to construct a 95% confidence interval. He found that 80 students have gone to the Taco Bell. I know, me and my Taco Bell questions. I deserve some Taco Bell. I've been trying to be good, but the Taco Bell. I don't care what it says. We're doing the Taco Bell. Cinnamon twists for Taco Bell are goated. I agree. And there's lava sauce. Dude, lava sauce at Taco Bell with like a chicken burrito or something. Lava sauce is goated. So with this full question, what is the first thing we usually do when we see a question? Here's Brian's steps for solving all these right here. We all deserve it, true. And when you solve a question like this, one of the first things I always ask you to do is
notation, brother.
Find the notation. So when you're finding your notation, it'll help direct you on which equations to use. Notation, brother. So you find the numbers. A lot of times the numbers are a good hint on the notation. Does anyone want to put any of the notation in the chat right now? See which of these values you can solve as I write the equation. Now, it's not going to be that quick of a solve because we're going to have to do one more step. And on the test, we would, in Stat Tool 1, give you a certain value right here that maybe I just wrote. You might know it from doing a bunch of these intervals. But what would it be? N is 200. Boom. Sample size right there. Anything else you see? See what else you can find. What else is there in this equation? Or what else can we solve for? But is p hat 95%? John's got very close, John, 1.96Z. The Z is 1.96. We would have to tell you that usually. And this value of 80, everyone forgets what it is, but what is 80? What is 80? And then we'll have this solved. So something happened here where p hat was found. So p hat is equal to 0.40, and q hat is equal to 0.60, because q hat is equal to 1 minus p hat is q hat. So 1 minus 0.4. But so I write that 1 minus 0.4 equals 0.6. That's 1 minus p hat equals q hat. So what is that value of 80? A lot of people forget that. Does anyone know? 80 is x. Yep. So don't worry, it's the most commonly. I think as like we use x for like other things like the x-axis, and I think people forget that we also use it for the amount of successes. So right here where we wrote x is the number of successes. How do we get 0.4? Great question. What is the math? Drop it in the chat if anyone knows it, and I'll start writing it out. But since p hat is equal to x over n, then we do 80 over 200 equals 0.4. Does that make sense? And x is equal to 80. Yep. I think Abby saw it too. Now Abby's like, oh, yeah, I see it. Once you see it, you're like, oh, I get it. And then you could also do 120 over 200. Great job. So now we can solve this. This literally becomes just plug the numbers in. It's just a plug the numbers in problem. We go 0.40 plus or minus 1.96 square root 0.4 times 0.6 over 200, and you solve. Questions could ask you things like, what is the margin of error? Questions, oh, thank you so much, Briley. You know what, Briley? Let's do it. Let's go crazy right here. Briley, 100,000 points. We've been going crazy. There you go. There's the SI link. It might be the same one. Might need to correct that. Thank you for posting that, Briley. I appreciate it. Thank you very much. So with this right here, let's solve first for the standard error. You should know this last component of the equation is the standard error. Make sure to get that right there. I love this class. If you can't tell, like, it's so nice that people can just like post things, and now we've got it pinned. It's very easy. 0.0346. That's the standard error times by 1.96. That's the margin of error now. So when you multiply it times the z-score, you get 0.0678. And then I'm just one step away from getting the interval. And the interval is going to be, if you round it to 7%, like you make your life nice. We'll just do that for the nicety of it. Now it's super easy. What's the lower and upper bound of this interval? What's the lower and upper bound of this interval? What's up, Ali? Good to see you there. What's the lower and upper bound? What's the lower to upper bound of this interval? In questions like this, we'd give you the z-score. Yep. And John's got it right there. You just simply add and subtract the values. So you just take the margin of error right here and add and subtract it to the estimate of what we believe is true. And then think about this. What are you trying to understand right here? Let's write confidence in the chat and see if you can fill it out, and then I'll say it for you. But great job, Riley and everyone. It's the interval goes from 33% to 47%. And how is the interval going to be talked about here? Mubot's got an interpretation in the chat. Think about this. I am a certain percent confident that the true whatever we are talking about is contained in the interval blank to blank. Briley's locked in. What is the interpretation here? Like, I am a certain percent confident. You just take the info from the question. When you interpret these things, you take the information from the question. We've done, this question does a lot of the knowledge. We are 95% confident that the true proportion of students that have been to the new Taco Bell is contained in it. That's it. Well, John, isn't it? I find it so easy once you know what to do. It's like you give your confidence, you give what you're talking about, and then you give the things. Now, I will say this. Be very careful, because sometimes it's true proportion, sometimes it's true mean, sometimes it's true difference. And great job right there, everyone, on the answers in the chat. The only thing we didn't check was the conditions. Did Brian randomly take a sample of UT students? He did. Did he take less than 10% of all UTK students? He did, because 200 is way less than 10% of all UTK students. And do we have at least 10 successes, at least 10 failures? We had 80 successes and we had 120 failures, because you subtract from 200 to get the remaining failures. 80 successes out of 200 remaining would be failures. And Liz, good to see you there. So with this, that has this first one done. Really good work, really good questions, kind of a nice review on it. So should we do tests next? Charlie wanted us to do some tests and talk about p-values. So we could do the one proportion, because we're kind of going in order. Is everyone ready to do some one proportion z-test? Who wants to do that? And it is success failure because exactly success failure is because of proportions. So let's do one proportion z-test theory. Okay, can you explain the first true false? Yeah, let's do that before we move on. So the only way, oops, I lost it. The only way to make a confidence interval more precise. Okay, what do we mean by precise? There's a word you should know, and Kahoot will be coming up at 2. What does precise mean? What does precise mean? We can do some true mean stuff too. But what does precise mean? If you hear precise, like your parents say, tell me precisely when you will get home. What does that mean? A what-er interval. Not necessarily more confident. Like your parents say, you say, I'll be home sometime tonight. Your parents say, be more precise. It can relate to smaller confidence, a narrower interval. So you are correct that it could relate to less confident, because you could be like, no, don't worry, it's practice. We're going to make the equation nice and big here on a new page and just take a look at this equation. Sure. So with this equation on a new page right now, let's look at it. There's my pen. P hat plus or minus z star p hat q hat over n. Now, while it's true that p hat and q hat are part of the margin of error, we really only focus in on the z and the n for how it affects the precision. Now, we are whatting by n. I'm trying to let you know that it's in the denominator, so we are whatting by n. We are whatting by n. I'm letting you know it's in the denominator of the equation. We are whatting by n. Very important to know when you look at this. We are whatting by n. We are dividing by it. So since we're dividing by n, if n goes up, then margin of error will go what? I'm going to put a color-coded version of this right here. If n goes up, margin of error will go what? Margin of error goes down because you're dividing by it. So if you increase the sample size, the interval gets narrower, i.e. more precise. But there's another way to change precision by changing how what you are. Another way to change precision is by changing how what you are. How confident you are. So if you decrease the confidence level, decreasing the confidence level will also in turn decrease the margin of error. But I want you to notice something. Since z is in the numerator and it's related to confidence, z has the same relationship to margin of error, as in if z increases, you get more confident, you get a wider interval. And if z decreases, it decreases the margin of error. Like an 80% confidence interval is more narrow than a 90%. 90% would be wider interval, less precise. So there's some, let me ask you this. Larger n is related to a what precise interval, more or less precise? So the question I'll write in the chat, larger n is related to a more or less precise interval. So which way is it? A larger n is related to a more or less precise interval. You can use the cheat sheet here. Be careful, because I could see how this could trick you. Because we're talking what happens to the margin of error. Be careful. I see what's happening. This is what's saying the margin of error. So answer this question. Don't worry. We got this. This is where we're making sure what we see right here. If I say the interval is more precise, it is whatter. Maybe you'll start to, like, once it clicks, you're like, oh. If I say the interval is more precise, it is wider or narrower. If I say the interval is more precise, is it wider or narrower? A more precise interval is a whatter interval. More precise. It's a whatter interval. More precise. More precise is a whatter interval. Is it wider or narrower? Smaller, right? It's narrower. It's tighter. So with that in mind, if you increase n, margin of error does what? And I'll answer that in a second, Maddie. If you increase n, yeah, Allie's got it. Allie's got the right attitude. I like that. If you increase n, then what? Like, make sure you know what happens. If you increase n, then this happens. And what does that mean? A larger n leads to a wider interval. A larger n leads to a what interval? Try to finish the sentence. I want you to say it and think through it. And I'll tell you the answer. John's got it. You see what John said right there? Look at this. John wrote it. Increasing n means you decrease the margin of error. And when you decrease the margin of error, the interval gets tighter. Like decreasing the margin of error means this, right? So, and Abby's starting to see it right there. Like increasing n makes the margin of error smaller. That's what this means right here. And if the margin of error is smaller, that means it is what? So finish the sentence, which John said it by saying narrower. So if you increase n, the margin of error goes down because you're dividing by n. So the interval is definitely what? More or less precise. Because the interval is doing this. What is it? Yep, more precise. Exactly. Does anyone feel like it clicked, I hope? It's just understand what precision means. Precision means tighter. And when you take more data, you'd have a better estimate, so your interval would get more precise. Imagine someone said to you, like, just think theoretically for a moment. Someone says, I want to figure out how good you are at basketball. Do you think they would have a better estimate from watching you shoot 5 free throws or 500 free throws? When would they have a better estimate about how good you are at basketball and make a more precise, like they're probably this good and be more precise in their estimate from watching you shoot 5 or 500 free throws? 500. So in that same theory, larger samples lead to better precision. Does that make sense? That's an even quicker, like mnemonic way to remember it, that with a larger sample, you have higher precision in your estimates. It also mathematically works out because the interval gets narrower, but then try to come up with an example right there. And then it's easy to remember with the z-scores from 68, 95, 99.7. When you get more confident, the interval gets what? More or less precise. So who can finish this next one? Great job, Maddie. As you get more confident, the interval gets more or less what? And I'm going to label this part of the video so people can come back to it, like precision and confidence. Exactly, Briley. Nice job. Because you're going 68, 95, 99.7. So if z-score increases, because you could flip these arrows right here. So they're related in the same direction. Like if z-score goes up, then that's going to be hard to flip that arrow because it's color-coded. But if z-score goes up, margin of error goes up, and it gets wider, it gets less precise. Because just think with your hands, 68, 95, it got wider, so less precise. But good, right? We're all morphed in. I like it. So exactly, more confident means less precise because the interval is wider. Exactly. Good memorization. Okay, next topic. I copy-pasted it so we can put it in the link right here. And please ask questions. I'm putting links for people to watch this in the future, but this is also for you. If you're here live, we'll be doing the Kahoot in 30 minutes. But I want you to ask questions. Okay, so this part of the video is confidence intervals. Oh, what am I doing? This part of the video is brought to you by a hypothesis test for the true proportion. A hypothesis test for the true proportion. Now we have a method we use in this class. Who knows the acronym of the method we use, which we're going to walk through and explain first? What is a hypothesis test? That'd be awesome, Riley. What is that? It's the HACS method we use in this class. So HACS method. It's just an acronym I made up to help remember it. If you got a better one, drop it in the comments. Always trying to find out mnemonics and ways to remember this and help you do the work. So the HACS method is hypothesis, annotate notation, which you can do first technically if you want, check conditions, and also solve and state. So solve and state. Annotate. Why can't I think how to spell annotate? I was just mad about that. So with this, let's talk about what a hypothesis test is. A hypothesis test is just that somebody believes some value is true to start. So someone has a belief about a value that they think is true. What do we mean by that? Brian says he believes, we won't make it Taco Bell related for once, Arby's. Because Arby's, they got the beef, right? Brian believes that over half of his students have tried Arby's. We can kind of do this right now. It's going to have a little bit of a problem. But let's not do Arby's. Everyone's had Arby's. Let's do In-N-Out Burger. So have you had In-N-Out Burger? So click the yes or no button in the chat for have you had In-N-Out Burger. We have the meats. Arby's is foul. I've started a war. Hopefully not Briley. My friend Nathan does, apparently. Apparently. I think the world's an oblate spheroid. So we have no In-N-Out Burger here in Knoxville, but man, I'd love to try some In-N-Out. Got some family out in California. So what we're doing right now is we're collecting data, and we can see what percent of people have tried In-N-Out from our sample. But notice how it starts out with the question. Let's write the question. The researcher decides the question and what they're researching. Does that make sense? This is almost one of those big teaching to the test moments, and go down to Murfreesboro to get some In-N-Out, it seems, in the future. So the researcher, not the data, decides the way we do the question. So Steak and Shake's good, but they're gone, are they? Brian believes that half of his students have tried In-N-Out burgers. He collects data and finds out. Let's find out what the data said. So here's the data I collected. Data says we only have 10 votes here. He collects data and finds out 7 out of 10 students have tried it. Okay. He collects data and finds out 7 out of 10 students have tried it. Is this evidence that more than 50% have tried it? Now I can answer this question. Do you think this is evidence? Yes or no? What do you think? There's also some issues we're going to have with this if you already see it. So, well, I mean, you'd say it's 70%, right? But think about in the simplest of case. What if I talk to one person? Like, Briley, have you had In-N-Out burgers? Have you? And Abigail's pointing to some issues we're going to run into for this problem. So I talk to one person. I say, Briley, have you tried In-N-Out burger? Have you? I talk to one person. And Briley has not. I say, man, no one's tried In-N-Out. I talked to one person. They haven't tried it. And do you see the problem? And this is what statistics is going to do for us. Statistics looks at kind of our sample and says, is what we saw in our sample unusual given the null is true? So what if I talk to 10 people, what is the most likely amount out of 10 to have tried In-N-Out? If I talk to 10 people, what is the most likely amount out of 10 people to have tried it if 50% is true? If 50% is true, what was the most? It would be 5, right? I mean, how far away did we land from 5? That's what statistics is going to analyze for us. So the first thing you have to do is you have to write your hypothesis. And we have a null hypothesis and we have an alternative hypothesis. So we have our null hypothesis and we have our alternative hypothesis. So the null is a statement of what Brian currently believes. And can anyone write it in the chat? It always has a population parameter, which is something we're testing, equal to a hypothesized value. So what is the null hypothesis? We need some parameter we are testing and then set it equal to. Very close, Abby. So you have the hypothesized value. That is true, but you're missing the parameter, and John's got the parameter. We're testing if the true proportion of people who've tried In-N-Out is equal to 5%. But it's not p hat, though, because we're seeing, is it true? And good work. I like this. Good work, everybody. Good practice. Because, and I'll give you a hint, for our tests, the answers to the parameter are either going to be p, or they're going to be mu, or they're going to be mu1 minus mu2. Where'd my mu's go? They're in my Pokemon. So these are the only parameters we use right here. In this class, there's other ones. And these are the different chapters we cover. You're not going to write a null that looks like this, but does everyone follow right here that like in the last chapter or chapter 17, we did the difference between the two means is 0. And then you can also test that the true mean is equal to something like, you could do the true mean is equal to 0.5, but usually it's not decimals, like true mean equal to 20 or something like that. So you pick from those, at least in our class. Are you testing the true proportion P, the true mean mu, or the true difference in means mu1 minus mu2? Good Pokemon. So we are testing this right here. The true proportion of students who have tried Taco Bell is 50%. The only thing that changes about the alternative is what? Because we want to see, is there evidence more than 50% have tried it? So the only thing that changes about the alternative, we should know this. You got that. I know if you'll know it. I'll do it. The only thing that changes is the sign. And it's the researcher's question that controls this. It's not by the data. You don't say, oh, more than 50% tried it in the data, so let's do that test. No, you do it by the researcher's question. Good test question there. So now we need to annotate notation. So who's got some notation for me? Help me annotate notation in this question, which is our next step to solving these. What is our notation that we have right here? What is the notation? What is the notation? N is 10. Correct. N is 10. Ooh, nice job. Riley's got X already. N, X, and then one very close, Riley. Very close. So, and we got P hat and Q hat. Good job. So X over N is 7 over 10 is P hat equal to 0.7. Q hat is 1 minus, which is 0.3. And very close on what this is. This is not P, though, because that would be the truth. How did that happen? It's a snap thing. That was funny. So it's not P, though. It's what? It's not P, though. It is P naught. P naught. Great job, Abby, right there. It's P naught. And you'd probably get it right. Like, it's very close to P. But it's the hypothesize. It's not the truth. It's what I hypothesize, which actually goes right here because P is equal to the hypothesized value. It is what P is equal to according to us, according to the null, and it's technically P naught right now. P naught, the hypothesized value. And Abigail was pointing out it is evil note. It's one of the most commonly forgotten ones too. The little naught on it. There's P hat, P naught, all those things. Set conditions. Condition 1, random. Condition 2, 10%. Did we take less than 10% of the population? And then success failure again. And so here is, be very careful. How many successes and failures did we have? Because this time the success failure condition is a little bit different. This time it's NP naught greater than or equal to 10 and NQ naught greater than or equal to 10. So how many successes and how many failures did we have? Do you know? It's either way we fail. I'll tell you that much. How many do we have? Very close, John. But here's the thing. It's P naught, though. And they're both 5. Bradley, yes. Yep. No, you did it. That was it. You just plug the numbers. Because remember how P naught and Q naught? Because if P naught is 0.5, Q naught is... You fail either way. Either way, you don't have enough. But you plug in 0.5 for both of these. You plug in 10. And yeah, W Bradley right there. And then you will get that these are each equal to 5. So you don't have at least 10 successes, at least 10 failures. So we technically fail that condition. And it's very similar. It's just you have to do it according to the null. So it's NP naught. The confidence interval uses NP hat because there is no hypothesized value for the confidence interval. It's just testing what we see in the data. But we can still run this test just for funsies. Why not? So let's solve this out right here. To solve out this equation, we are going to do P hat minus P naught over P naught Q naught over N square root. I like to point this out every time we talk about confidence intervals. Every confidence interval is always a what? Whatized. Not confidence interval, excuse me. Every statistical test is always the what. Like, what does this represent? A what up top. And then we whatize it. Which actually leads to what is called a test statistic. And then I'm going to give you one more big theory thing which I haven't talked about nearly enough. It's standardizing. We standardize the difference. And you can see this at different standards. Yep, because y bar minus mu naught over s over square root of n. That's the T1. or we have the other T1, which is y bar 1 minus y bar 2, which is just the difference between the sample means, over the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Or we could do observed minus expected squared over expected, which is still just a different standardized. And that is equal to a singular cell chi-squared, to which you sum them up. So you notice the theme of all of these, that they're just a difference up top in the equation, and then you standardize that difference. That literally is showing the green. You standardize the difference, and that leads to a test statistic right there. So we're just going to plug in our numbers. Those were other equations for other parts of the test. We're not going to use them right now. Just theoretically understanding this. And so we plug in the numbers. Why are we doing T if it's the proportion? Oh, we're not. Good question. Those were just examples. We're doing Z. Good question. Abigail, let's throw Abigail 100,000 points. I didn't mean to lead to confusion, but Abigail, you are 100% or 100,000 points correct right there. We're going to throw a few more bonuses, but that was a good question, and you are correct. We will not use the T for proportions because Mr. T is mean. Proportions are not. And unless you're doing drugs. Well, don't do drugs. But you are very, very correct. This is a Z-score because it deals with proportions. And so now we put in the sample proportion of 0.7. We minus the hypothesized proportion of 0.50. We multiply by P naught times Q naught over N square root. And then we just solve out right here. The bottom is the standard deviation technically. I know you're waiting for me to say standard error, but the bottom is actually a standard deviation because it's based on a hypothesized truth. And the Z-score, if you look at this, is going to be about 1.23 or so. That's 0.20 up top. 1.26, I was kind of close. So the Z-score is equal to 1.26, and we are doing a greater than test. So we really shouldn't, we should say we violated conditions and we shouldn't be doing this, but it's going to look like, it's going to look over here, and it's going to be a big area. It's going to be somewhere around like 15% of the curve. And on this point, we wouldn't have you solve this on the test. So we would have you like find the Z-score, and then we wouldn't have you solve it because you can't get the p-value on the test without an applet. So here's the applet, and we go to the above. How do we know which way to shade the curve? How do we know which way to shade the curve? Why am I shading above? How do I know this? How do I know which way to shade the curve? Oh, I was a little bit off on my p-value guesses today. How do we know which way to shade? The way we shade the curve is decided by what? How do we know which way to shade the curve? Based on the sign of the alternative hypothesis. Since this is a greater than test, you shade to the right of the test statistic that you landed at. So you go to the test statistic and shade to the right of it, just like you can see in this question right here. I just type in the test statistic and shade to the right of it. I should have known 1.2816 is the Z-score for 10%. 1.2816, I can't type. That's the 10% right there. So I should have guessed a little bit closer to the actual answer. So with this in mind, what is our conclusion using the 0.05 alpha? And we should all know this. So think about what we would state right here. First, I'd probably say we can't do this because we didn't do enough. We didn't have enough successes and failures. But what is our conclusion? You what the null. Now, Mubot's about to put this in the chat. We're going to copy paste it, but there's only two choices to make. You either what or what the null. And I'm going to highlight stuff right here. Our p-value was equal to 0.107. And good to see you, Chloe, right there. We will fail to reject correct. And I want you to notice the way I have this organized. If you think of this as a choose your own adventure, I'm making two paths for you right here. So when you reject the null, you have evidence for the alternative. And that's why you're rejecting the null, because you're saying, I believe something else. If you don't reject the null, it's because you don't have evidence for the alternative. And I like to say don't reject. What is another way that people say do not reject that you got to know? You probably should know this. What is another way that people say that they don't reject? What is another way that people say they don't reject? Oh, I shouldn't have done this. Fail to reject. fail to reject. They say I failed to reject the null, which just means like I failed to go to the mall today. I didn't go to the mall yet because my p-value of is then this means front house state alternative again. So let me recolor this real quick. So here it is. Greater than, do not. Okay. Greater than or equal to, greater than, exactly. Okay. So the way this would go, and good to see Ashlyn, is once again, our p-value is 1.107. Can't be 1.07. I do not reject the null that 50% of students have been to In-N-Out Burger because my p-value of 1.107 is greater than my alpha level of 0.05. This means I do not have evidence for my alternative that more than 50% of students have gone to Taco Bell. Notice when I'm stating the alternative in the null, I'm just reading this. I do not reject my null that the true proportion of students who have gone to Taco Bell is equal to 50% because my p-value of 0.107 is higher than my alpha of 0.05. This means I do not have evidence for my alternative that the true proportion of students who have been to Taco Bell is greater than 50%. Who follows this right here? Who feels like maybe you're starting to get the stats down? You're starting to be like, I see it. I get it. I get it, maybe. I get it. I hope. I failed. Nice job, Abigail, right there. I failed rejecting all the 50% of students have been. In-N-Out. We're doing In-N-Out right now. Because my p-value of 0.107 is greater than my alpha level of 0.05. This means I do not have evidence for the alternative that more than 50%. Yeah. Just understanding what you're saying right here, that you're stating your conclusion. Yeah, that's what happens. 200 characters max. And I'm going to try to do one more thing right here. Let's put this. I want to put this in the video because we have like 10 more minutes before the Kahoot. This is not a yap. Yeah, yeah. Confidence interval and tests. Okay. So let me write two equations for you. Here's two equations, and you're going to see something. This is the equation for the confidence interval for the true proportion. This is the equation for a proportion test, a one proportion z test. Now, what do you notice is different about the z? What do you notice is different about the z? What do you notice is different about the z in these? Is there any difference anywhere with the z? What do you notice is different? Do you notice the difference? You should see it. There's a star, right? Wait a minute. This one has a star. So the reason there's a star on the confidence interval is because you decide the z-score based on what? So this means you decide it. Who's next? You decide. Epic Stat Tool 1. It means when it comes to the confidence, you can say Z is 1, 68% confidence. Z is 2, 95% confidence. Epic. Briley, of course, knows. I'm going to give you guys and gals and pals something here to watch after this. We'll do this. It's got 109 million views. We'll see you get copyright claim from. They're not going to hit. But you decide this right here. And then this one down here, my favorite is chapter 13, I think, where you are like, oh yeah, I do say that. That's a lot of work. I was trying to do it. I did like 3 takes of it, and I was like, it's not happening. It's not happening. You know what it's from, right, Riley? You know the epic rap battles of history. Can we chip in money to have you recreate an epic rap battles? I wanted to epic rap battle. We'll take a break because we've done a lot right now. And this, I want you to know that this Z and this Z are different. You pick that Z right there, and the bottom one. Oh, you didn't know of epic rap battles of history? So here, we're going to show this because this is really good for everyone to just learn about. So this is what okay. What is it called? Nice Steve or something? Do not hit us with a copyright. We're going to drop this link for everyone. Not that you need another view. You've got 109 million views. So please don't copyright claim us. We're giving you shout outs. And I think, give me a yes if you can hear this. You ready? Here we go.
My name is Skrillex.
It's so good. If I play the whole thing, I'm gonna get in trouble. I'm gonna get. No, I don't think it's in Russian, is it? It's not in Russian, is it? It's so good. Don't copyright claim me. What the heck is that doing in Russian? Why is my closed caption? 2 seconds here. What's going on? Why is? How did that happen? Did they close? I don't know what's going on. Okay.
My name is Skrillex, man. Welcome to the Devil's Den. I'm a scary monster up in this Sprite and frilly pan. You're a weirdo, Wolfie. You're into powdered wigs and poo.
It is insane. Like I love remember when Kids React tried to copyright React? Oh, I do remember that. That was like 2016 or 15. Wow, I'm glad you remember that. It was like 2016, 2017. Like I love Mozart's stuff in here. Please don't copyright us. We're gonna drop the link. We're not trying to make money off this. I won't monetize this video. We're not trying to make money. I played a little. This is a shout out to Epic Rap Battles. I've spoofed it. Check out my spoofs of your videos.
I'm the world's greatest composer. No one knows what you are except a lonely little troll who knows how to press a space bar. I attack, you decay. Can't sustain my releases. Sidechain, wolf game. Bangarang you to pieces. I'm a self-made man. You're a slave.
It's just crazy. Check out Epic Rap Battles. There's a whole bunch that are in here. There's some videos we have ads on, not this one, but I'm gonna drop this in here. So check out Epic Rap Battles of History. They are the best. My wife and I have seen like so many of these. They're all so good. And this is my top. One of my favorite ones. It's so good. But yeah, it amazes me. I know Ball anime rap battles were in my time. Oh, I don't know that one. Dragon Ball or something? I should know that. But just the reactions, the script, that means very, very loud. Fortissimo. Yeah, like from piano to fortissimo. So it's being a musician myself. What is it? You don't I might know it. I might know it. Sometimes I forget what I know. We're just taking a chill right now. We're gonna start the Kahoot coming up here. Let's go to the main screen. Epic Rap Battle, we might have showed up. So if anyone does YouTube here, you actually get a copyright claim if someone uses your material and it shows up in your studio, and then you can see like what they used it. Like one time I invited a speedrunner and he speedran Mario, and then I get all these like things that people are using my video because he did Mario. And yeah, and then sometimes people do false copyright claims on your video to be like, this is my video, but it's not their video. It's a mess sometimes, but please don't hit us. We're supporting you guys over there, Epic Rap Battles. Make more, then we'll stop using your videos. If you used it, you'd be like, statistics, I know. Oh yeah, I should check that out. My middle school history teacher taught us about figureheads through these rap battles. That's awesome, Abigail. Like that sounds like you had a really great, that is a great way. I wish more teachers would do that. Really, I think we should try to incorporate fun stuff like that. It's got some light humor in it, but it's so good. Like there's like some jabs that are like historical jabs within it. Like you're like, oh, that person, yeah, it's very historical. So I guess we're about to start the Kahoot. Right? How many people we got watching now? Who's all here in the chat? We're gonna start the Kahoot. Let me put out a link saying Kahoot starting soon. Kahoot. Now I'm hearing myself to say Kahoot. Hair's getting so long. Clutching my Kahoot pearls. All right. We have 22 watching. Kahoot starting. Glad I logged in before too. Nice. Good to see you, Working Bird, right there. We're watching some Epic Rap Battles of History. Maddie's ready. We do have prizes for first, second, third. It's just one of those hair days. It's gonna be. I was outside in the cold for a long time. TN Voice, it's looking a little bit better. Listen, Kahoot starting soon. And link. Let me look at. We got to the 1 point level. And let me look at it again now, see if it's gone up. We currently are at 69%. We can do better though. 69. I have 2 students who didn't do it, and it's like 100 students haven't done it yet. We usually get 2 points, and I'm just like bummed. I'm like, come on, let's do it. I'm just gonna, I don't know. Spam ping everyone on Discord. I do that a lot. I think I do that a little too much. Well, let me get the Kahoot up here in the background. A fun Kahoot. How many points can we get? Up to 3 points from the TN voice. So Kahoot starting soon. Sorry. Oh, I've been so tired lately. Who is ready for break? I have a presentation tomorrow night, and then I'm done. I'll be so happy when I'm done. People better lock in on TN voice. I hope so too. What are the other places we can get bonuses for besides YouTube? A lot of, I haven't added in all the bonuses from like start of the semester, things like that. So there's a bunch of bonuses. So yeah. Can we get a bonus breakdown? There's like the surveys at the start. There's the TN voice. I'll be going through and cleaning up everything, making sure all bonuses are added in. It usually adds up to about 2 points maximum. The big bonus is the Mubot bonus. Mubot bonus is where it's at. Jude's here and saying hey to Mubot. Mubot bonus is where it's at. That is the bonus you really want to get, which you can get pretty easily, I think, by being in class. We've been very generous with Mubot bonus. We have those new levels. So the Mubot should be here. Is not saying hey to people? Where's Mubot? He's here, right? There he is. There he is. I was all worried. I was like, where the heck is Mubot? Did he go away? I don't want Mubot going away. Okay. Let me get exam 3. We'll be Kahooting here really soon. Mubot did not greet me. We have beef. If you get here too early, Mubot might have beef too. So you never know. You never know. So there he goes. There he goes, Greedy. Look at that. Look at that right there. Mubot in the chat. Okay, so let's get exam 3 going here. Exam 3 review session. Exam 3 review. 26 questions. I think this is the right one. This looks good. This looks good. This looks good. Hey. Post live. Ooh. A little tired. Got up early this morning for coffee and conversation. A lot of good talk. Oh, well, we got a winter island. What? Okay, let's go over and start the Kahoot. Okay, we're not taking attendance, so we can jump into this. Okay, I need a nap. I do. Tell Vicky to run an energy drink up here. Vicky don't have Vicky do that. Don't have Vicky do that. Shouts to Vicky at the Vol Shop and shouts to Trinity. What is Coffee and Conversation is something held for faculty and I think just faculty. But it's where we get to sit down with the provost and oh, dude, that sounds nice. I've been trying to lay off them, but that sounds nice. So the provost hosts something where they have conversation with faculty and listen to our concerns and what we're thinking. And it really is a great time. Huge thank you to the provost office, Heather over there, and of course, Provost Zomchak. But they do a great job of listening to us and actually inviting us out to share our thoughts, and they're very receptive to them. One thing I brought up this morning that I thought was really helpful for safety and security on campus, and just having an open forum for people to voice concerns. So huge thank you where we can share concerns and get them heard and get them addressed, and yeah, very productive. So that's what you need. If people can't talk, then they can't fix things. So if you're like, hey, I think there's an issue, and they're like, we're going to fix that. We're going to look into that. So, yeah, making sure our campus is as best as it can be. I wasn't able to, oh, there's no email on this one. But I want to say this also. And I gave this person a shout out yesterday. I'm going to give him another shout out today. Let me go look him up again. We got to give a shout out to the man, the myth, the legend. Hey. Here we go. We're going to pin him right here. Does anyone know Collin Zimmer, UTK Elf? Who knows Collin Zimmer? We'll bring this down here in a second. But Collin Zimmer, UTK Elf, doing awesome things. He's awesome. Everyone loves Collin. So he is awesome. This only has.
Students are pushing.
Here, wait, do this right here real quick.
Are push.
I want you to go to this video, 386 views, and I want people to go to this video. If you're watching this now in the future, we're gonna put a bookmark on this. Kahoot, and I'll bring the link back up here in a second. Collin is awesome. So go to this video. My friend screamed in the quiet room when he stuck up. That's so funny. Collin is awesome. Collin is one of the many reasons why UTK is awesome. And so there we go. So there we go. Add something. Random videos. Add something to the video if you want, but give Collin a shout out. We'll put the link back up here. But if you want, give him some W's, spread the cheer, spread the positivity. It means a lot to me when students go out of their way to do positive things for other people. I think he said he ordered 30,000 candy canes. A lot. And he got a new elf costume this year. Embodiment. And even there was a band playing yesterday on Ped Walkway. And then they went down and migrated towards where he was at, and they were just next to it because he had a speaker and he was playing Christmas music. So then it was like, well, wait a minute, let's combine our powers right here. Let's like Captain Planet this, or that's Wonder Twins. Let's by our powers combined. Now we're like super awesome, like an elf with, you know, handing out Christmas candy, and also, and he's done other things. He's done Easter and a bunch of other things. Really just means a lot that he does that. So huge thank you to Collin right there. We'll get started in about 1 minute. So tell your friends to do that, to join in. Send the link. Be like, hey, you can Kahoot with us. Yeah, that's what he sounds like. What? So if you see him, throw him some positivity. Be like, thank you so much. You're awesome. Even don't take a candy cane. Be like, thank you. I mean, I think it's just nice to be nice. There's so much rage bait out there. Nailin Thunder. What's that? Is that an energy drink? I need to try it. There's so much rage bait. We need nice bait. We figured that out in class. Welp. Let me put the 30-second timer on, and then we're starting. 30-second timer. Any other thoughts? What are your thoughts? Do we need more nice bait in the world? Nice bait for the win. The quote of the day right there. Quote of the day. One more quote of the day at least. Quote number 564. Nice bait. Yeah, we need to. That needs to be the word for 2026. Like, you tricked me into feeling good. You tricked me into being happy. You baited me into it. So I think you need a space right there. It'll do it with the space. Oh, I did 465. I don't even know what I'm doing. Who knows what quote that is? I need to stop hitting things on my desk. Have you not seen his speedruns? Oh, wow. Who knows what that was from? From previous semester. Someone said that. Okay. 30-second quote one. I think that's Stat Nation or Stats is awesome or something. Stat Nation. Have you got a chance? Could you check out the Discord? A couple questions. Yeah, I'll do it after this, Jude. I'll probably go home after this, probably eat a little, and I'll check it out. So it will be responded to. Thank you so much. Brian's biggest loser, but we're all winners. Quote of the day. Because sometimes I do like paired. Was that from when I used to do paired t-test? Oh man. Cool. I want to see a few more quotes when we get started. Notation brother. That's from Leo. That's classic. Everyone knows that one. These are all quotes from the History of Stats 1. I'm gonna look at one more, or I don't know if we should have one more appearing, right? Maybe not. If you do quote, he does a random quote. So if you just do quote, it just picks from the random 564 quotes that we have from like everything. I saw Mubot on the field confirmed. I can't even remember who said that. I think they said Mubot was playing or something, but there's 500 plus quotes from what people have said that has cracked me up. F in the chat for future quitters. Okay. So check out I am not like Zoom problem. Oh, wasn't Zoom problem guy from our chat? Remember there was Zoom, like, I'm Zoom problem guy. That's our semester. Sorry, I'm getting distracted. We're going to start here. But I'm Zoom problem guys from our semester. That is quote 560. That's quote 560. Yeah. So these are all, you're in the history. I have a dream where all tiny Brian's get to live free. Okay. All right, we're going to start here. Let's do this. Time to start the Kahoot. Let's do this. Statue of Raphael versus, well, let's make one more quote here, but we're starting the Kahoot. First question in the Kahoot is going to be, how do we test to see if there's a relationship between being married and not married and a student's age? This is a categorical variable and a quantitative variable. This goes to tools and techniques. How do you test this right here? So think about, what graphic you would make to test this. What graphic would you make? What graphic would you make? So, who has an idea in the chat? What kind of graphic would you make to test this? Well, you have if a student is married or not married, right? Close, close. When do you use a mosaic plot? When do you use a mosaic plot? So mosaic plot looks like this. Mosaic plot is when they're both categorical. But we have married and not married. And then we have age. So you do this, and you would do what with these? So this is where you have categorical, categorical, but we're not doing that. We're doing categorical, quantitative, and we're going to compare the whats. We're going to compare the whats. You can see the answer down there. You could compare IQRs. Good answer here right there. You could compare IQRs. That is very true. But think why it's called a two-sample t-test. Because Mr. T is what? The two-sample t-test, we're going to compare the means. We're going to compare the means. So you compare the mean for this one versus the mean and do a comparison of mu married versus mu not married. So the two-sample t-test has a categorical and a quantitative. We can expand upon this real briefly right here, where if you're doing the chi-squared, it's two categorical variables. If you're doing the t-test, it's just one quantitative. So something like age could be a t-test. Something like age, this is the two-sample t, so this is two-sample t, and then two categoricals is chi-squared. This is the t-test right here. And then the only one I'm missing right now is the one proportion, which would look like if we graphed it out like a bar chart, like the proportion of people who owns pets, yes or no. And that would be one categorical variable. So this is age, which is quantitative, which goes with the T. Is this color coding helping anybody? How are people doing on this? And this is one categorical variable with yes, no. It has two levels, but this would be a one proportion. This would be one proportion Z. So there's the, yeah, the color coding I think helps a lot. So these are the differences in the tests. What are the univariate tests? What are the univariate tests? What are the univariate tests on the screen? What are the univariate tests? What are the univariate tests? Not the chi-squared though. Good answer. The top two. Good answers. The t-test and the one proportion, because you're just testing someone's age, or you're just testing if someone owns a pet. Like this could be own a pet. And then the bivariate tests down here have two variables. So they have two things. I guess I'll circle the chi-squared and the two-sample t, because you're comparing. Does that univariate means just one variable is being analyzed? Like we're just analyzing someone's age. We're just analyzing if they own a pet. So we're not analyzing age and owning a pet. We're analyzing what is the average age of a UT student. We're analyzing do students own pets, yes or no. So the yes or no is not two variables. It's just do you own a pet, yes or no. Yeah, no, really good practice. Univariate means one variable is being analyzed. Bivariate means like does living on or off campus, is it independent of owning a pet? Is there a relationship or is there a difference in the average age of someone who's married versus not married? Apparently married people are younger. I didn't know that. But really good stuff right here, really good practice. And that's got a summary of that whole question. That was a big little mini lecture right there. Great job, lovely Condor. Let's do the next question. Keep asking questions. Here we go. How can we test a relationship between someone owning a pet and if they're married? You got this. I know you got this. Who can put in the chat what this is related to? This is related to the what? What condition for this? What is this condition called? Oh, we already have a mosaic. You're right. It's related to mosaic. And with both these variables being this is actually the what condition. Because for this, we have condition two categorical known as what condition? Hint, I'm not blocking the right answer. So the two categorical variables is actually called the count data condition. The count data condition. It's kind of like success failure, but it's called count data. What are the 4 conditions for this test? What are the 4 conditions? Can anyone give the 4 conditions? This is your time to practice. See if you can write them down. Condition 1 and 2 are easy. Condition 1. Ooh. Wow. Random. Condition 2, 10%. Less than 10% is sampled. Then we pause when we get to condition 3. And I want to point this out. If you're watching this video right now and you need review, the biggest thing this video helps, and this is more like to see where you're at, and great job right there. Count close. I think we're seeing some, and there's review 3. We're going to pull up the review right here. And this video down here at the bottom is excellent because I go through all the conditions.
This is one proportion.
I'm saying a billion times. This video is 6 years ago. 6 years ago. That was me 6 years ago. And there's all the conditions. So the conditions at the end here are, we have the expected cell counts are greater than or equal to 5 and the count data. Success failure is if it's categorical. And I've still done some color coding up here where nearly normal is for quantitative data and independent means is when you have 2 means. So the last conditions are expected cell counts greater than 5 and also count data. Expected cell count is when we do row total times column total over grand total, and we need all those to be greater than or equal to 5. Check out some of our recent live office hours, and we did quite a few of those, especially yesterday's. We were doing tons of expected cell counts. We might still have some of those documents open, but the expected cell counts are what you solve when doing the chi-squared test of independence. And, oh man, I must have closed them off. So the expected cell counts, solve them, and then you will see if there are at least 5 or more. You're welcome. Yeah, we did a ton yesterday. It was really good office hours. Good work. Okay, let's do the next question. Keep asking things. Lovely Condor in the lead, Winged Yeti and Friendly Crow, and Golden Viper and Mystery Oryx. I used Excel to solve a question and got it wrong. How? No, let me take a look at that. Send it to me and I'll take a look. When doing a hypothesis test on the mean, what is a condition that must be met? Which is a condition that must be met? Hypothesis test on the mean. Send it to me and I'll take a look. I fixed up quite a few of them for people. So a hypothesis test on the mean has what 3rd condition? You just saw them. I could have put random and 10% and you'd get it right. You'd be like, random, 10%. Those are always the first 2 conditions. And then when we get down to the 3rd condition, we have to pause. That's not a condition. But we pause to slow our minds to get the right condition. Since this is quantitative data, we could make a histogram. So think since it's quantitative, oh, that's all right. Since it's quantitative, we want the data to look how? When doing t-tests or t-intervals, you want your data, which is quantitative, to look how? Does anyone want to put the word in the chat? Nearly normal. Mr. T, who's mean if you're doing drugs. We all know that. So we want the data to look nearly normal, which can be checked by looking at the histogram. It can't be checked by degrees of freedom greater than 10. Lots of ways to check. Good to see there, Will. And so we got it right there. Success failure is for categorical data for like proportion tests. So check out the conditions. And the other 2 over here are for chi-squared. These are chi-squared condition 3 and 4 respectively. And that is for proportion tests on the bottom. And then the nearly normal is for quantitative data. Okay, Lovely Condor, Winged Yeti, Friendly Crow, Golden Viper, and Mystery Orcs. Next question. Which condition do we need at least 5 of? Good review question on this right here, too. Which condition do we need at least 5 of? And we could solve this out. I'll give you a version of this right now. Brian tells you he went to the store and bought 50 candy bars. 50 candy bars. Brian went to the store and bought 50 candy bars. Now, of the 50 candy bars Brian bought, 10 are chocolate and 40 are vanilla. Can't add. With these, half the candy bars have nuts and half the candy bars don't have nuts. How many chocolate candy bars do you expect to have nuts? Who can figure it out? The answer is row total times column total over grand total to figure it out. But you could actually theoretically find it too. Not 30,000, true. So think, but half the candy bars have nuts and half don't. How many chocolate candy bars? You got it, John. So with this right here, you could do it by doing row total times column total over grand total. And you could solve this math out. You just circle them, multiply, and you get 250 over 50 equals 5. But did anyone think who thought theoretically, well, if half the candy bars have nuts and Brian bought 10, I'd expect half the 10 to have nuts. Does that make sense? That's what you're doing. When it says 5, does it mean 5? It means at least 5 here, which we technically have at least. That'd be 5, 5, 20, 20. It means these numbers in the expected counts. These are not how many we see. I expect 5 of the chocolate bars to have nuts. I expect 5 of the chocolates not to have nuts. I expect 20 of the vanilla to have nuts. I expect 20 of the vanillas to have nuts. Or not have nuts, whatever I didn't say. But here's what you might see. You might see something like this. And we'll put here nuts and no nuts. Does this look weird to you? Who thinks this looks weird? Like Brian bought an imbalance of the candy bars. So all the chocolate candy bars have nuts, where less than half the vanilla candy bars have nuts. Good to see you, Lauren. And so this would mean there's probably some association. And if you viewed this visually, it would look something like in a mosaic plot, which we'd like to pair with this. We'd have the chocolate where there's less chocolate bars, right? Because there's only 10 chocolate bars. It might even be a little less than this. It might be more like this, 10 chocolate bars and vanilla. All the chocolates are going to have nuts, and the vanillas are going to have about this many nuts. So this will be the nuts right there. And then the no nuts. Does that make sense, what I'm saying right here? That you'd be like, there looks like a strong association where all the chocolate candy bars have nuts, and then less than 50% of the vanilla bars had nuts in them. So this appears to be an association. We could run the test, the chi-squared test of independence, to say the chocolate bar having nuts is not independent of what kind of chocolate bar it was. There's an association. And we want there to be at least 5 expected cell counts. But that's the observed. Good question right there, Riley. This is what you observe. The expected is based, so you don't even need these numbers right here because the expected is based off the what's. So finish this sentence. Who can finish it? The expected is based off the what's. When you solve for what the expected value is, it's based off the what. The values inside of here are the observed. This is what you see. It's actually the totals. So the expected is a mathematical calculation where you could say, imagine this. Brian teaches 200 students, and half of his students are athletes. So you know that half of Brian's students are athletes, 100 students are athletes. And then half of his students love K-pop. So 100 students love K-pop. How many of the 100 athletes would you expect to like K-pop? So half of Brian's students are athletes. He has 200 students. Half of them love K-pop. How many of Brian's students who are athletes would you expect to like K-pop? How many would you expect? Well, 25% of the total, that is true. And the way this one would look, I'll draw it out real quickly, is what we'd have right here is we'd say Brian has 200 students, and we know that half are athletes. So we have athlete and not athlete. We have K-pop and not K-pop. And so we have 100 athletes, 100 who like K-pop, and 100 who don't like K-pop. And so what you would do to solve this is to figure out the expected. You'd say 100 row total times column total over grand total. And then you can also think theoretically about it too, to be like, well, if half the people like K-pop and half are athletes, you could say I'd expect this many. And you can solve this to get the expected. But that's not then what we see. What we see is maybe that athletes love, everyone knows athletes love K-pop, that it turns out the athletes who love K-pop, 90 athletes love K-pop, and there's only 10 who don't. And then 10 of the non-athletes like K-pop and 90 don't. So does that make sense? Like, this is what you see in the data. So this is not the expecteds or anything. This is the observed data. So this is what you observe. The percentages on the outside help you figure out the expected by random chance if there is no relationship. Kind of a mini lecture there almost. These values in the other colors get you the expected values. And then the observed values are what you see. Like, I see 90 athletes like K-pop. So there we go. Good questions. I like it. Okay, Lovely Condor, Winged Yeti, Friendly Crow, Mystery Orcs, and Jubilant Tapir. Which of the following must be met for the chi-square test of independence? So there might be multi-select here. Good review. Which of the following must be met for the chi-squared test of independence? How do we write the null? What would the null hypothesis be for athletes and liking K-pop? For the chi-squared test of independence, the null for athletes and K-pop would be what? What would be the null? What would be the null hypothesis for athletes and K-pop? Who knows? The trick is you just put the word independent between it. Being an athlete is independent of liking K-pop. Exactly, Ben, right there. You said it. All you do is you go right here and put independent between whatever you're talking about. And that's got it. You just do that like being... What about the chocolate bars and nuts? What about the chocolate bars and nuts? So put that one in the chat real quick. What about the chocolate bars and nuts? Liking K-pop is independent of being an athlete. Exactly. Being an athlete is independent of liking K-pop versus not independent, which is the alternative, we're looking for an association with the alternative. The candy bar one is the type of candy bar is independent of it having nuts, or having nuts is independent of the type of candy bar. And then the alternative would be the type of candy bar is associated with it having nuts. You must like K-pop. True. Facts right there. We'll do one more quote of the day. You must like K-pop. We don't think we have many K-pop quotes. So whatever's on the vertical axis is the it can go vice versa. Usually I think they say X is independent of Y, but if X is independent of Y, Y is independent of X. Good question, Ben, right there. So it can be X is independent of Y or Y is independent of X. Quote 556. Quote 556. That is the first K-pop quote for our class. The first K-pop quote. Wonder if there is. Nope. Yeah, it's the first one, I think. Why don't we have others? Okay, the other two right here, success failure, is only for categorical data, for proportions, not just for categorical. And then the nearly normal is for quantitative data. Nearly normal is for quantitative data. We need a D-Dragon soundboard for chapter 18. Oh, yeah. Remind me of that. I'll try to edit on there and we'll get it. Then it'll copyright claim us. Lovely Condor, Winged Yeti, Mystery Orcs, Friendly Crow, and Jubilant Tapir. The chi-square test of independent statistic is found how? We got this one. Here's a hint. If you get a question like this, look at the formula sheet. Look at the formula sheet. Let's drop the formula sheet in the chat right here. If you don't know the answer right now, look at the formula sheet. So if you're reviewing with us, open up the formula sheet. You could get a question. You get to print the formula sheet. You're going to see the answer. Here we go to formula sheet. You get to print this. Wait a minute. Who wants to yell it out? Look at this. This is the chi-squared test statistic, which is found by doing this. There's that row total times column total over grand total. And these are the cell chi-squareds, which if you do this, you get the right answer. So there's the answer. Hopefully a lot of people get it. But the answer, we just saw it on the screen. Make sure to read over your formula sheet. It's a huge help. I think I'm blocking the right answer. The chi-squared test of independence Pearson test statistic is found by summing the cell chi-squareds. And please, 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 please look over the formula sheet. The sum of all these cell chi-squareds is going to be the chi-squared test statistic. That has it right there. Good job. Okay, Lovely Condor in the lead still. Is it something because we are dividing by the expected values? It's not really relational to that. Good question. It's just summing because each cell gives, we'll see some output here in a moment, but each cell gives a cell discrepancy, and then you add up all the cell discrepancies to get the total discrepancy. Think of when you do the test, each one of these, I've made a mess of the screen, but each one of these cells will come up with a discrepancy. So each one of these has a discrepancy value. So then to figure out how much discrepancy there is, You merely add together all of these values, and you get the total discrepancy when you get the cell discrepancies. So each cell has its own discrepancy, known as a cell chi-squared, but when you sum the cell chi-squared, you get the total discrepancy of the test. Does that make sense? So one of these is a cell chi-squared when you solve it. And check out yesterday's office hours, like Abby was saying right there, really helpful. And I know it's tough because this is like the last chapter we just did. So you get cell chi-squareds, and then you add them up to get the total discrepancy. So it's how much total discrepancy there is. Okay, what is your decision regarding the null? I know you got this. I know you got this. Take a look at that. What is your decision? Do not click the bad words. Who wants to say the bad word in the chat that you shouldn't say, that if you see that on the test, you're like, nope. We got a mnemonic for this coming up to help you remember it. What's the bad word? Yeah, I know. Office hours. Thank you so much, Abby, right there. Mebot even telling him. Accept. Oh, no, we do not accept the null. We do not accept the alternative. We have a saying here, when the p-value is low, reject the null. When the p-value is high, just let it fly. People are like, stop clapping in the mic. Reptar, good to see you. So when the p-value is low, reject the null. When the p-value is high, just let it fly. Not in this class. So look right here. The p-value is high. Just let it fly. What does let it fly mean? What is that? Huh? So what does let it fly mean? Let it fly means fail to reject. Fail to reject. When the p-value is low, reject the null. When the p-value is high, just let it fly. Fail to reject means do not reject. Because what you saw on this test was likely given the null is true. And when you think about this, which of these looks likely? Like Brian says to you that your test is independent of your grade. Would you imagine you look at the people who get A's on a test and you look at version A and version B, and it looks something like this. Like these are people who got A's, or we'll do pass fail. These are people who pass. These are people who fail. And you see something like this. These differences look to be what? I'll show that again, Rose, here in a second. I'll show the p-value. I'll point to exactly where it was at. These differences look to be very big or small. And I'm talking about right here. These differences look to be very what? I'd say small, right? But imagine you hear this is how it looks. Here's version A. What happened with version B over here? Version B, everyone's failing apparently. This would probably have a p-value something like this. And this would have a p-value something like this. I'm just making it up. But with this p-value over here, this is telling you that the differences observed are what? The differences observed, someone finished my sentences, are what? These differences that we see between this, and don't give me version B on the right side. The differences we observe are what? On the left side, the one I've circled right here, the differences we observe are what? Well, are they statistic? Well, what does statistically significant mean? Are they statistically significant? They're not significant, which means what? These differences up here are likely what? Those differences, they're not significant. They are likely by what? So the differences are not significant. They are likely by random. When you look at this, does that make sense to say that? If you said to someone, look, I know that there's a difference between those tests, but it's very small and likely by random chance. That's what that p-value means. But think about what this p-value means. The differences over here are basically impossible by what? These differences here are basically impossible by what? Virtually impossible. I could have made the p-value even smaller. Let's do that. The p-value is saying to us that these differences are virtually what? They're virtually impossible by random chance. Now it's like a 1 in a billion chance that this would occur. If the tests are truly independent of passing and failing, then these differences should not occur. They're virtually impossible. So I don't think that the tests are independent of passing. I think there's a relationship to passing the test with which version you take, because the differences here are virtually impossible by random chance. So a high p-value means the differences you observe are likely by random chance. So this would mean likely by random chance differences. And this would mean unlikely. And think what unlikely means. It means low p-value because that's what unlikely means, and this means high p-value. So the differences observed there are likely by random chance. The differences observed here are unlikely by random chance. And the p-value is right here, prob, because p-values are probabilities. Thank you, Rose, for asking. So prob right there of the Pearson chi-squared test statistic, it's this number 0.5609. 0.5609. Good questions. Lovely Condor, Mystery Oryx, Friendly Crow, Mighty Dugong, and is that a Pokemon? Winged Yeti. Let's do this. So, like a self-proclaimed exactly the ones we do in class. Like when he runs a 502 or she, whoever runs a 502, you're like, well, I don't reject the null because that's a likely difference by random chance for a 5-minute mile runner. But when they run a 1502, you reject it. How high is high p-value likely? So a high p-value is one that is bigger than what? Good question, Charlie. A high p-value in statistical words is one that is whatter than what? When a p-value is high, we say p-values are usually 0.05, which is the considered alpha unless otherwise stated. So a p-value that is high is higher than 0.05, which is the alpha level unless otherwise stated. So alpha, which is the point at which we reject, most statisticians or people use 0.05, which is a 5% type 1 error rate. Okay. How many degrees of freedom does this test have? How many degrees of freedom? Brian, this is a what by what. I should not put 90 seconds on here. Let's talk about degrees of freedom as we do this question. This is the chi-squared test of independence. How do you know that? How do you know this? Workenberg, great work. This is a chi-squared because you see a mosaic plot. Does it say it too? Probably says it. It says the degrees of freedom too. It's the chart, the mosaic plot, right? The mosaic plot. So mosaic plots right there are for two categorical variables. And this is a 2 by 2. If you delete one row, delete one column, you get 1 times 1. How about if we did freshman, sophomore, junior, senior, and the state you live in out of the 50 states? How many degrees of freedom would there be? That one you can't do with your hand. And then I'm going to answer Charlie's question here. If we did freshman, sophomore, junior, senior, and then out of the 50 states, kind of curious. Well, you're on the right track. But what do we do? So it's rows -1 times columns -1. So you can do the freshman, sophomore, junior, senior. Who knows? I'm having to think this one through. I'll do an easier one next. Yes, that's the degrees of freedom. 3 times 49. Yep, it's 147. So make sure to times them though. Rows -1 times columns -1. I think it's 147 degrees of freedom. How about if we did? I picked between Arby's, McDonald's, Taco Bell, and In-N-Out, 4 restaurants, and to see if that's associated with your class level 4 things. How many degrees of freedom? Your calculator lied to you. So we go between 4 restaurants and 4 class levels. How many degrees of freedom are there? This one you can do with your hands. 9. Yeah, you just 3 times 3 is 9. You just literally delete. You say you delete one row, delete one column, and there's 9 degrees of freedom. And Charlie said, can you explain it again? Why is high p-value more likely by random chance? And good question, Charlie. So that goes into the definition of a p-value because the p-value is the probability of our results by random chance. So when we have a high p-value, it means that it's more likely. So it literally is a probability. So when we see a high p-value, it means more likely by random chance because it's a probability. Like this is like a 48% probability that our results are by random chance. So it's more likely than this one, which only has a 1 in like a billion chance of being our results occurring by random chance. So this one is more likely to occur by random chance. This one is less likely. And it just has to go with the value of it because it has a higher probability. So higher probability equates to more likely by random chance. And that's what a p-value is defined as, is the probability of your results by random chance. Good to see you, Jonathan. And we got some work going on. Let's do it. Figure math on stats final. Exactly. The stuff you learn in grade school helps. Lovely Condor, Mystery Oryx, Friendly Crow, Winged Yeti, and Mighty Dugong. What is the null for this test? You got this. Some chapter 19. I'm going to give you 2 other null hypotheses for you to practice if you've gotten this one. So go ahead and solve this one. There's a trick for this. Let's do the 2 other in the chat right now. I'm going to disappear so you can see it. No, I'm blocking an answer hint. Okay. Write the null hypothesis for Brian wants to test if 60% of students are from Tennessee. Write the null. This one requires statistical notation. Brian wants to see if 60% of students are from Tennessee. So what's the null? When you write a null, you give the parameter, equals, and then some value. The null will have the equal sign in all but this test. Boom, John's done it. The proportion of students from Tennessee is 60%. And Abigail did the null hypothesis states the proportion of students is 60%. And if we had you writing it out, either one should be acceptable. Technically, Abigail gave an A+ answer worth 100,000 points, and John, too, contributing in. I like it. So let's try this one. How about Brian believes the average student spends $20 a week outside a meal plan. Brian believes the average student spends $20 a week outside a meal plan. So low p-value is less likely by random chance and is more significant. True. Yes. Lower means more significant and less likely by random chance. Brian believes the average student spends $20 per week outside meal plan. Exactly. And this one switches Kira right here. It's no longer P. It's mu because it's quantitative. So mu means quantitative. Does that, how are people doing on that? Mu is for quantitative. Great job right there, Kira. So the null states the true mean of dollars spent is equal to 20. So low p-value is less likely by random chance and is more statistically significant. True. Low p-values are less likely by random chance and more statistically significant. So this is a lower p-value and is less likely by random chance and more significant because lower p-values are more significant. And when we say statistically significant, we mean less likely by random chance. Good questions. Isn't the null always saying that the variables are independent? Not always. That's when we do the chi-squared test of independence. When you do the chi-squared test of independence, which is chapter 19, we simply put independent between the two things right here. Gender is independent of breaking a bone, and we see it right there. The alternative is going to be gender is not independent of breaking a bone. So independent null is only for the chi-squared. For the others, we will use the following format. Let's write it out. So the following format for the other ones is to do the following. You'll write out the null states, just like here, and then you'll pick from one of the following, either P, mu, or mu1 minus mu2. Then you'll put the equal sign, and then you'll put the hypothesized value. Down here on the alternative, you'll simply carry over whatever you put here and whatever you put here, but you'll pick the sign. So try this. What about if I asked you, who's smarter, UT students or Florida students? And let's see if there's a difference. So what would the null hypothesis be to see if there's a difference in intelligence level between Florida and UT students? Who can write this one out using this? You're only going to select one of these, and whatever you select will be carried down. Then we need the hypothesized value, and that'll also get carried down. And then we select right here. So what do we do? What would it be? Is there a difference in IQ of UT? Well, it is mu. It's because we're measuring IQ, so it's quantitative, and we're comparing UT and Florida students. Ah, Kira, nice job. It's going to be mu1 minus mu2, and we could write mu T versus mu Florida, and then we hypothesize that there is no difference. So we hypothesize there is no difference. And then we see if the difference between UT minus Florida, if the difference is not equal to 0. Does that make sense? Who follows this and are like, okay. We're comparing two means. Exactly. We're comparing the average UT high IQ versus the average Florida IQ. I do hope we win. We've got a lot riding on this. But you pick, like if we do the proportion one, where we said the proportion of students from Tennessee is like 70%. So then you would go here and you'd choose proportion. And maybe you're thinking it's increased in recent years. So you want to see, has the proportion of UT students increased from 70%? So it'd be 70% over here, and the proportion is, we can make this bigger. The proportion is greater than 70. Last question on this. For 100,000 points, what is this in notation right now? Who can tell us in notation? That stands for the hypothesized true proportion. So what is that in notation? A lot of people forget this one. What is that in notation? For 100,000 points, last question on this. It is P0. It's P0. It is P0. P0 is the hypothesized, is P0. So in technical terms, the hypothesized value when you're doing this, the hypothesized value is going to be one of the following. It's either going to be P naught, mu naught, or 0. And that's associated with each one of these. Like P has P naught. I shouldn't highlight that comma there. P is associated with P naught. Mu, the true mean, is associated with the hypothesized true mean. Although you can test differences other than 0, when we test the difference between two means, we often hypothesize the difference is 0. So many P naughts in the chat, but that is the hypothesized true proportion. Good stuff. Covering a lot of ground with the material right now. Here we go. Lovely Condor still in the lead. Next question. What is the alternative for this test? You got it. Nice and easy. Writing the null is so easy. All you have to do for the alternative is put not in front of it. I'm going to wake up. Wake up, Bran. It's 2015. What is that thing? Wake up. Wake up, it's 2001. You just got Pokemon Silver as a gift. Wake up, bro. It's 2001. Oh, it's just like multiple? Oh, it might be. Let's take a look at that. I got distracted. So there are other ways of phrasing it. So when you think about the alternative, there's not just one way of phrasing the alternative. The alternative can be phrased in multiple ways. So think about these that are synonymous. Because the null, right there, Hutton knows. So the null could be that gender is independent of breaking a bone, which could be gender is not associated with breaking a bone. Like, gender, what does that have to do with breaking a bone? That's what the null says. The null could also be gender is not related to breaking a bone, or gender is not dependent on breaking a bone, which also means independent. It looks like we're picking the best Pokemon. Red Blue is good, and classic Red Blue. So Black and White 2, Sun and Moon was all the ones. Now they got like all, what do we got? Sapphire, Ruby, Emerald. Too many. It's like multiple Pokemon games. Good work. Okay, so we missed. Not everyone said gender is associated. Black and White, good ones right there. So gender is associated with breaking a bone, and that is the same thing as saying they. Oh, good. No one's like. Not many selected that one because we're not comparing means. This is categorical. Gender is independent of breaking bones. It's kind of the classic way of doing it. And then gender is associated. You could also say gender is related to breaking a bone. I teach classes in R. Definitely will. A lot of my classes I teach in R. I use R a lot, so I code in R. So you might see some R. Tell me, do you code in R? Let me know. Lovely Condor, Mystery Orcs, Friendly Crow, Mighty Dugong, and Winged Yeti. All in the lead still. Great work. Find the missing value. Game guide for silver. Nice. That's awesome right there, Hutton. So what value are we missing here? We are missing a what value? Who wants to say in the chat, and I'll start to solve it. We are missing which value? And there's a super quick way to solve this that you can solve it in seconds with multiple choice. A lot of times it's numeric entry on the test. Yeah, well, let me know. That's what we teach. That's what we teach in. We are missing the expected value. See how it says expected right there? We're missing the expected. And so let's take a look. So since we're missing the expected value formula is row total times column total over grand total. So what do? We have to find the row total. We have to find the column total. That works too. That's a very quick right there. And Margaret knows. Margaret knows the tricks. We have to find the grand total. And then we simply multiply them together and divide by. So I like these two. It's kind of like a Sudoku puzzle. And there you go. Kira, you got this. Look at this. And if you solve that out, you'll get it. And you can also add these up right here, which a lot of people have noticed. Because when you add these up, you can add them up to this right here. They would have to add up to that. Or you could add up everything in the table. Row total times column total over grand total. Yesterday's office hours. Make this half the exam. Once you know how to do them, they're pretty easy. You just have to know what you're solving for. You're just like, and you get the formulas. Let's put the review 3 in the chat again. But you get the formulas, so you don't actually have to memorize them. The formulas are right here. The expected cell counts, that's what you're trying to solve right there, is row total times column total over grand total. What is another name for the counts of the data? They're also called the what values. The counts of the data are also called, think of an O word. What's another name for the counts? Which are the top values in this matrix of values. They're also called sometimes the what? Observed, the observation, the observed. So when we do observed minus expected square of expected, might help for the next question. You use those values right there. So good work. Really good answers on the question. Let's do the leaderboard. Lovely Condor still in the lead. Next question. Find the missing value. What do we got? You are missing a cell chi-squared. Go to the formula sheet. On the formula sheet. On the formula sheet, the formula for the cell chi-squared is observed minus expected quantity squared over expected. And this is equal to a chi-squared of a cell. And so you have to go into these, and you have to take the observed value, which is going to be this. This is the same thing as count. It's a synonymous word. And then you take the expected value, which is that. That's just the expected. And you have to divide by the expected here. And so the top part of this test is just a what? Like all other tests, the top part of a test is just a what? Like all of the other tests that we do, the top part of the test is just a what? Like all other tests we do, it's just a difference. So the top part is a difference, and then the bottom part standardizes it. I'm just writing other tests we do, and this creates a test statistic like that. Like this is a test statistic, this is a test statistic, the T is a test statistic, this standardizes it. So these are just other tests we do and how they relate to the same formulaic idea, and we get a test statistic from this. Had to whip out the calc for that. Yeah, observed minus expected over expected. It was going to be 416 over something. So it's a, yeah, if you take this and you do 128 minus 131.895, that's going to equal to 3.895 squared over 131.895. And that is equal to, there's the number right there. So it's equal to. So good work. It's so easy to, I know once I started doing them in Excel, I'm like, this is just easy. Like you just put it in and solve the answers. It was nice and easy. I'll have to check out office hours. Yeah, office hours were really good on it, Jude. Yesterday, we did a lot of work and a lot of practice, and we just kept solving them. And I think if you went through yesterday's office hours, you got it down really well. I think education's really tough. Like teaching has changed a lot, especially with AI. And we have so many conversations of how do we get our students to learn? What expectations do we have? What do we require them to? It's so interesting now because pedagogy has changed, like how you teach. That's what a pedagogy is, pedagogical methods. It's very tough. We should totally have access. There's maybe ways. We might do that in the future. But man, teaching got tougher. What are the degrees of freedom for the one sample T interval? You got this. This is a one sample T. We're going to repeat how to get the degrees of freedom here coming up after this quick question. Brought to you by your sponsors. Jude knows. The one sample T has n minus 1 degrees of freedom. One sample T, n minus 1. Two sample T, it's what? Two sample T, it's what? Really? There we go. Too complicated. So 2 sample T, the degrees of freedom formula is too complicated. And what we mean by that is the degrees of freedom formula is, it's this mess over here. There you go. There it is. So the one sample T, degrees of freedom, n minus 1. 2 sample T, too complicated. And then the last time we do degrees of freedom is when? What is the last time we do degrees of freedom? What is the last time we do it? It's all right, Brad. Chi-squared. And that is equal to rows minus 1 times columns minus 1. And do you get this information? Do you get this information? Degrees of freedom for the mean test, which is a one sample t. There's 3 times in this class. There are more ways to use it, but 3 times. The one sample t is n minus 1. The 2 sample t is too complicated right here. The 2 sample t is 2. And you can do it for confidence intervals or tests. So there are multiple ways to use the 2 sample t for confidence intervals or tests. And then the degrees of freedom for the chi-squared are rows minus 1 times columns minus 1. So make sure to have your formula sheet out and know the parts it has on it, but also memorizing them a little bit doesn't hurt. It really helps to just kind of keep them in your head right there. Great questions, everybody. Okay, leaderboard, lovely Condor. Here we go. What is the missing p-value? Ooh, these trip people up. These trip people up. How many alternatives are there? How many alternatives? You can see them over here. But how many are there? How many alternatives are there? Let's use this for a tiny bit longer. Okay, let's talk about how to solve this. There are 3 alternatives. The greater than, the less than, the does not equals. When you do a statistical test, you will land somewhere on the curve. Where you land is your test statistic. So this is like your z-score. Now, if you do a greater than test, you'll graph to the right of it. I just want to make this a little bit better. Sure that. Oh, that's way better. You'll graph to the right of this because that's the way it points. You graph to the left of this because that's the way it points. I like to say this one you graph both sides, which means you graph above this point, and then you do a reverse image and you graph below. And it might not look perfect, but I tried. So with this, and yep, so think about this. These 2 p-values right here have to add up to what? What do the 2 p-values right there have to add up to? The 2 p-values here have to add up to what? Like, let's say the top one is 30%. They have to add up to 1. So what's the next p-value? The next p-value is what? The next p-value is what? Because it's like, if you add them, they add up to 100% of the curve. So the next p-value is 0.70. So the less than and the greater than add up to 1. Like if you add them up, they equal up to 1. But how about this one right here, which is merely a reflection of this over to the other side? It's double the what? The does not equals alternative is double the what or p-value. Smallest. So what is the does not equals p-value going to be? I might not have drawn it perfectly, but it's going to be equal to what? So what's it going to be? What is going to... You got this. For this test, it's going to be what? Yep. Yep. So it's going to be 0.60. So let's look at our result here. Nodal appeal got it. Don't worry. But look at how it works. So this is the does not equals p-value. But look, wait, this is the less than. What is a quick solve on this to get the missing p-value on this? To get the missing p-value, what would you do? And it rounds. If you look at it, it rounds. What would you do to get the missing p-value? Just do 1 minus, right? Because this is the greater than, this is the less than. These are the 2 that if you add them up, they have to add up to 1. This is the does not equals p-value. So you just do 1 minus, and you get basically this right here, which rounds to 0.0021. So let's see. Lovely Condor. We still got a good leaderboard. How do you know the does not equals 2? Let's take a look at the next one, because maybe it's a review question. I sound like I'm about to like, everyone gets review questions. So the does not equals is the greater than absolute value of t. And it's always what of this p-values down here. So the missing p-value now is the does not equals 1 because it's greater than the absolute value of t, which means t could be positive or negative. So how do you get the does not equals p-value? You take the whatist and you what it. Here's the does not equals. And how do you get its p-value? How do you get it? Is there a review question right here to Charlie's question? Double the smallest. There it is. You just reflect this on the other side. That's it. That's it. Yeah. You could try doubling either of them, but remember, p-values can't go outside 1, so you can't double the bigger one. So the way it works when you do this is, like, imagine we have to go use the applet. Let's try solving this with the applet, which can be done. So to solve this with the applet, what am I going to have to put into my applet first? Using the T applet, every T has what's with it. Every single T created by William Gossett has a what to it. Every T has a what. Every T you ever get must have what's. You must enter in the what's to begin. Every T you enter in the what to begin. Degrees of freedom, right? So there are in this, because it's the 2 sample T with the weird degrees of freedom formula, 722.53. So degrees of freedom are 722.53. And if you notice, it looks like the normal curve. So what I'm going to do now is I'm going to take the T statistic right here of negative 2.8794. And we're going to find the p-value. And we're going to do the outside test. We're going to put in negative 2.7894, I think it was. Oh, I messed that up. There we go. 2.7894. 2.8794. And then we're going to do the positive version because this is the absolute value on the other side. And here is the p-value right there. So there is the p-value that we got, 0.0041. I think that was on the previous output, though. But here's the p-value right here. And we could even do some more decimals to it. But that is the p-value right there. Can we get... It's a quote. A cat named... Actually, that's a funny story. I'll tell you that another time. A cat named Quant visited, I think, last year. It was a horror show. I'll find that video. Could I do that? I could try here in a moment to bring back a cat named Quant. We'll do that at the end. Remind me, Working Bird or someone. We'll try to bring back a cat named Quant. That's a fun story. Let me say this. I like to think my teaching is, what do you think the ratio is of fun to learning in this class? Like, for Jude and everyone else here, I know some people enjoy it. Some people, maybe I'm too much. What would you say the ratio of fun to learning is? Like, what % of the time do we have fun? What % of the time do we learn? Try to separate it. Like, learning isn't fun. Everyone knows that. To a certain extent, it's not. But I mean, well, don't do 100-100. Like, if you had to break it apart, like, what % of the time is spent off topic? Because there's off topic. I know there's off topic. Everyone knows there's off topic. But what % of the time... Truest opinions. Of course, your name's attached to it right now, so it's not anonymous. But what % of the time is off topic? I appreciate the mini breaks too, because your brain can't focus more than like 5-10 minutes without a break. And which way does it go, Jude? 30% fun and craziness, 70% learning, or is it 30% learning, 70% fun? Yeah, I'd hope I keep like a 30-70 split. I think some people think it's more like the other way, but maybe they're just coming in at the wrong times of class. Yeah, exactly. You can't stay focused for... There's no way to run an hour 15 class where you're just like totally focused the whole time. You can only morb in for so long. You got to morb out. So I like to throw in a little bit of fun. We'll show a cat named Quant here at the end because I forgot about that. I want each class to have their own unique experience and get to know the students, get to meet people. If you see me on campus, say hey. I've already met quite a few students here. I met Jeremiah at the start of the semester, Briley, tons of students who come by office hours. So I know Trinity. Just seeing everybody is awesome. So if you see me on campus, be like, hey, what's up, Brian? I'll be like, hey, what's up? Be like, I was in your class, but that's awesome. Osby and Haslam. Haslam's awesome. But we have to have a little bit of off topic like we just did now. And I really appreciate it because what's the point of learning things if you're not enjoying yourself? So there we go. Let's do it. What is the missing T ratio? The T ratio is going to be the difference divided by the standard error. Did you hear that? The T ratio is the difference divided by the standard error. The difference divided by the standard error. So when you see the absolute value of T, that means the does not equals alternative. True. That is the p-value of the does not equals alternative. If you heard what I said right there, remember our formula? I'll write it over here on the side. If you take a look at the formula, here's the formula for the t-test. You ready? It's y bar 1 minus y bar 2, which is a difference. That's a difference. And then it's over square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2, which is equal to a standard error of the difference. Did anyone figure this out yet? Did anyone figure this out? They keep me locked in Haslam. Well, the difference, right? Do you see a difference? Do you see a standard error of the difference? Difference? A standard error? You can also cheat over here. Wait a minute, look where this is at. You go out 1, 2, 3. That's about where the curve ends. You got 4, 5, 6, 7, 8, 9, 10. Remember the normal curve with the 68, 95 within 2, 99.7. If you go out to the end of the curve, that's basically 3, and then you got to go another 3 and another 3 and a little more. There it is down there. Oh, it's all right. It was negative. The difference was negative, so the t-score is going to be negative. Oh, the good question right there, Briley. So this one didn't. This is like it's a tough like theoretical question. We might have changed up how we ask it, but this right here, y bar 1 minus y bar 2 is the difference. So this value here, I'll highlight. I'll take this. So y bar 1, y bar 2 aren't on the screen. This quantity is y bar 1 minus y bar 2. So that quantity is the difference in the means. And then, no, y bar 1's not the difference. This whole thing right here is the difference in the means. That's what it means. That's the difference. Does that make sense? And then this quantity here is the standard error. And so that quantity right there is the full thing of square root s sub 1 squared. How do you get the answer from this then? Who knows how to get the answer? Just what? Just take the numbers and what? Because it's hard to draw that. You could, that one's possible. You have to give you all the numbers, Jonathan. This one Nabila's got it. This one you don't really calculate it. You're just given the standard error. So this is the standard error, like already solved for you. Like this is that value right there. I think people understand this now, right? Who feels like they understand what that is right there? So the t ratio would just be dividing these numbers, and it's basically negative 10-ish, about negative 10, because they're the ratio of the two numbers, which is the test statistic t. Okay, next leaderboard, lovely Condor. Here we go. What is the missing value of the difference? It's just a review question right here to see if you remember and you're paying attention, because you see how the t ratio here is going to be the difference of these divided. So it's y bar 1 minus y bar 2, the difference over the standard error. And I'm trying to think and I will be doing more review. We've changed up the test a little bit and we don't have as much jump output. This is jump output. I still think you need to understand it. I want to point that this is differences in GPAs for males and females. So since the difference is negative, what does that mean about male or female GPAs? We observed what? Since the difference was negative, remember it was like negative 0.23. What does that mean about the difference in GPAs? What does that mean? Exactly. Because when the difference is negative, the second mean was higher in the sample. And what does this mean now that the interval does not contain 0? Apparently, right, Rose? What does it mean since the interval does not contain 0? Since the interval does not contain 0, you would what the value of 0? Because remember, the null would be the true mean of male GPA minus the true mean of female GPA is equal to 0. Well, look at the interval. The interval does not contain 0, and here's the p-value of the does not equals test. So what do you do to the idea of there being no difference? You what it. You what it. Because, the p-value for the does not equals test is that. You reject the null. So what would you conclude? I have evidence what? I reject the null, and the interval shows that female GPA is somewhere between 8.18 to 0.27 higher than male GPA on average. That's the average female GPA is about 0.18 to 0.27 points higher. We reject the null. We have evidence of a difference that females have on average a different or higher GPA according to the interval. Conclude that females, and we could test for higher. And then technically if we test for higher, technically we'd have to redo the test. So right now the way the test is written, to get the right p-value, we need to test males have lower GPAs, which would mean this, which is the same thing as females have higher GPAs. So the way it's written with the signs, because who follows me right here, you could rewrite the math to be mu male less than mu female. So mu male equal mu female. And that's why this sign right there is this. just with the way this is written, with the ordering of male, female, you have to then, does anyone follow that? If you do male minus female, then you'd be testing male less than female, which is the same as female greater than male. And we do have evidence that the male average GPA is less than female GPA. So, oh no. Does anyone know? Don't worry. Thank you. So the sign down there is the sign of the alternative. And you can literally just do this. Check this out. You can just write mu male minus mu female equals 0. And that's the null. Because the null is mu male minus mu female equals 0. But mathematically speaking, if you have... This is what I did to change it now. This is an equivalency right here. If we take... You see how we could add to both sides of this plus mu female? What happens if we add plus mu female to both sides? On the left side, what? On the left side, what? If you add mu female to both sides, on the left side, that will what? Oh, God. On the left side, that will what? If you add mu female to both sides, on the left side, that will do what now? So we have mu male minus mu female plus mu female. On the left side, that will do what? It'll cancel, right? Because you're saying like add and subtract the same value. And then since you're doing 0 plus this, it's just this. So you see how, does everyone see how I've rearranged it? So it's the same thing to write mu male minus mu female equals 0, because that says they have no difference. If you think about what it means to say mu male minus mu female equals 0 is to say there is no difference, which is the same thing as mu male equals mu female, which would be there's no difference. Because you can just add this over to the other side of it, and it's an equality. Does that make sense? Sometimes I don't do every single math step. I actually got in trouble in I got in trouble in math class one time. They said, "How'd you solve this?" I said, "I did it in my head." And they said, "Do this problem." They had me do it, and they're like, "Oh, I guess he did it in his head." I was like, "I didn't realize it, but I think they thought I cheated." I was like, "I did it in my head." Like, what? We can do those in our head, but I love mental math. I think you've learned that from this, but I love solving math problems. They're so much fun. And then I try to remember, like, not everyone sees numbers. Ask me to do grammar. That's my weak point. Like, there, Brian. I say, what? You don't get the joke, man. Okay, lovely Condor. Mystery Orcs. Next question. What is the null hypothesis for this test? What is the null for this test? Okay, you got it. We just reviewed it. This is the 2-sample T. And there is a trick for this. Oh, gosh. I used to be better. I'll tell you, it's true and it's sad that the older you get, it's true, the slower you get to some degree. I mean, I used to be better and faster and quicker at math. It's, miss it. Crime to not solve it out. True. I can't do long division. I do long division in my head before doing it. Like, give me 2 numbers and ask me to divide them, and I'll try to do it in my head. Give me 2 numbers, ask me to divide them, I'll do it in my head. I won't do long division. This hint for this one right here is the null has the equal sign. The null has the equal sign. 356 divided by 38350. So, oh, so that's easy right there. That's easy. So if to Jude's one, that's 148.83. 148.83. 3 repeating. There we go. That one's easy. To Briley's one, well, you want me to reverse that? Because that's going to be a fraction. Briley's, if I had to guesstimate it, is going to be, the way we're dividing right now, is going to be about 0.087. I think Briley's is 0.087. If we had to guesstimate Briley's. 0.087. No, 0.092. 0.092. 0.092. 0.092. It rounds, but I was close enough. 12 okay, there we go. No, well, that's why I said Briley right there. 0.092. It rounds up, but we're close enough. I like mental math. It's fun stuff. It's fun stuff to do. Like, you gotta learn, like, the seventh is a beautiful fraction. The seventh is 0.1428, a seventh, which is kind of like how sevenths work. 7, 14, 21, 28. Sevenths are beautiful. Ninths are beautiful because ninths are 0.111, 2, 3, 4. Ninths are beautiful. And then what else? The 11ths are interesting too. They're 09, 09, 09, 09, 09, 09, 09, 09, 09, 09, 09. I think that's what it is. Yeah, those are interesting. I just think numbers are neat. They're neat. Beautiful is definitely reduced. All right, next question. Less about me, more about you. Lovely Condor, Mystery Orcs, Remarkable Dragonfly. Good to see you here. Friendly Crow, you were in third. You're still doing great, though. And Mighty Dugong, let's do some more learning. What is the alternative hypothesis for the two-sided test? What is the alternative hypothesis for the two-sided test? The two-sided test right here has the does not equals alternative. And hints for the test, a little teaching the test right now. We have three alternatives to the test. We have the less than, the greater than, and the does not equals. And who decides this? Is it going to be the data or the researcher? Almost one of these teaching to the test moments. Is it the data decides it or the researcher decides the alternative? The data or the researcher? You know this. It is the researcher, not the data. Don't get that wrong on the test. The researcher decides it when they're setting up their test, which way they do the shading. And that determines the alternative, determines the shading. So if you do the less than test, you shade to the left. If you do the greater than test, you shade to the right. If you do the does not equals test, you shade both sides. And yeah, the does not equals test is the does not equals sign right there. Shouldn't have done this one this long. I want to say a huge thank you. I guess I get a little wacky on 2-hour mark. We talked about fun. But yeah. This is the two-sample T. What kind of variables are in a two-sample T? Almost like that's another test question. What kind of variables are in a two-sample T? Is it quantitative, quantitative? Is it categorical, categorical? So you can see some answers. We're testing the GPA of students, I think, again. Jude said it. It's categorical for two groups and quantitative to compare the means of the two groups because t-tests compare the means, or if it's one t-test, you're just looking at the mean. Quantitative is going to be a regression, so we'd fit the regression line. Categorical is chi-squared. Okay, lovely Condor in the lead. Next question. Interpret the difference. We kind of did this one. I've ruined some questions. Interpret the difference. So we're talking about GPAs right here. If you weren't here for the last one, when the difference is negative, that means a certain thing. And you can see the difference right here. So we're looking at GPAs of males minus females. The only way to get a negative difference is if females are wetter than males. So think like 20 minus 18, would that be negative? 20 minus 22, would that be negative? The only way to get a negative difference is if females are what to males. The only way to get a negative difference is to see if females are what to males. If females are greater than males, true. So that would mean on average, females, and males would have to be less, like 18 minus 20 would be a negative difference. So no worries, Briley. So this would mean on average, and this doesn't deal with proportions because we're dealing with Mr. T. So it would be that on average, females have a higher GPA than males. And once again, the t-test, what's our saying? Let's say it one more time so we remember that it doesn't deal with proportions. Mr. T is what if you're doing drugs? T is not proportions. Mr. T is what? We love the guy. Great guy. Mr. T, legend. He's mean, though, if you're doing drugs. He's gonna bring some, like, fatherly energy mean. Like, disappointed in you mean. Not like me mean. You know what I mean. Mean if you're doing drugs. Mr. T is calling the cops on you. Lovely Condor, Mystery Orcs, Friendly Crow. Let's do this. Back in third. Story time. You walk through the woods, and the null hypothesis you have is that all of these things are twigs. And you make a type 1 error. What does this mean to make a type 1 error? So you have to know what a type 1 error is and watch and learn. In a type 1 error, this is a 1. What letter am I making, everyone in the chat? What letter is this? In a type 1 error, what? In a type 1 error, what? In a type 1 error, what? Gotta memorize it. In a type 1 error. True, it is a false positive. Yes, that is true, Working Bird. The null is true. That's what we're writing right here. We're saying in a type 1 error, the null is true. If the null is true, what does that mean about the world right now? So just look at this. The null is that it's a twig. So what does that mean? Someone explain to me what's true about the world. So you step on this thing right here. You step on it. And you're like, ah! So what's true about it? What's true? Like, tell me the truth of the world. You step on this thing, and what's the truth of the world? That thing right there, that big thing through there, you're like, oh my gosh. Wait a minute, it is, oh my gosh. But remember, the null is true. The null is that it's a twig. So the null is that it's a twig, right? And the null is true. The null is true. That is a fact. It is a fact of the world that comports with reality that it is a twig. But what do you do in a type 1 error? In a type 1 error, John's getting it. The null is true, but we what it? But we what it? But we what it? The null is true. You're walking through, you're just stepping on a bunch of stuff, you crack and feel something. The null is true, and we reject it. Has anyone ever done that? You ever freak out in the woods? You're like, ah! And your friend's like, what? You're like, I thought it was a snake. You're like, that thing? It's not a snake. So that's right there. It's a false positive. You think it's a snake, but it's not. Did you get it, Jude? I hope you got it right. The type 1 error on this would be a false positive. So think about a false positive is reacting to something thinking it's a snake when it's not. Does that make sense? So in a type 1 error, the null is true. It is a fact that it's not a snake. It's a twig. Oh, sorry. That's why I put up here the null is that it's a twig. Sorry. The next one's also one of these, but the null is stated up top, and the null is what you believe without evidence. So think about this. When you're walking through the woods, you usually go, that's a snake, that's a snake, that's a snake. I'm going to reject unless I have evidence it's not a snake. Or do you walk through the woods and most things on the ground are not snakes? You're like, I need evidence of a snake before I believe it's a snake. So you could set it up if you're a really fearful person, probably like me, where you would be like, I need evidence all these are not snakes before I walk through. But a lot of people usually want the evidence of snakes. So the null would be, because, and here's a good thing to know too, the evidence-based alternative, let me not say the answer. The evidence-based hypothesis is the null alternative, which requires evidence. Which of these requires evidence? The null or the alternative? Which requires evidence? The null or the alternative? Who knows? Not that. Go away. Stop it. Who knows? The alternative is the evidence-based claim. The alternative is the evidence-based claim. Exactly. You would need evidence that these are snakes. You're going to believe everything's not a snake until you have evidence it's a snake. Good work. Here we go. Lovely Condor, Mystery Orcs, Friendly Crow, Winged Yeti, and Mighty Dugong. Here we go. Story time. The null hypothesis is that the tree is healthy. What the heck happened? You made a what error here? You made a type 2 error, and the answer is kind of indicative in the picture, so I guess I gave it away. But think about this. In a type 2 error, the null is what, and we what it. Who wants to finish off that sentence? And notice that this is a 2, and this is in F, and this is another F, because in the type 2 error, we say this word twice. Well, it's kind of not the same word, but it's word starts with F. In a type 1 error, the null is can I type 2 error in Trinity, rewrite it real quick. Maybe there's a typo. In a type 1 error, the null is true and we reject it. And in a type 2 error, the null is false and we fail to reject it. So in the type 2 error, the null is false and we failed to reject it. I think Trinity basically has it right there. So does the null or alternative require evidence? It is the alternative that requires evidence. The null does not. The null is what you believe. I walk around my lawn, I'm like, my trees are healthy. And then I see one start to lean. I'm like, that's evidence that that tree is not healthy. I reject the null. So what would happen if someone made a type 1 error across their whole lawn? Does anyone know what would happen if you made a type 1 error? In a type 1 error, the null is true. The tree is healthy, but you reject the null. So what would happen to your lawn if you made type 1 errors everywhere? What would happen? No more trees. It's like Thanos. Half the trees are gone. So half type 1 errors. But with this, you cut down all the healthy trees. Exactly. Even in that, it's not that you're cutting down trees that are bad. In a type 1 error, the tree is healthy, but you chop it down because you reject that the tree is healthy. In a type 2 error, it's false that the tree is healthy, so the tree is sick, but you fail to reject that, so you keep it up, and the tree falls on your house. You leave the tree up and it falls is the type 2 error because the null is false, the tree is not healthy, but you fail to reject the null. You continue to believe the tree is healthy when you shouldn't. And this can happen. This happens all the time with errors in tests. You sometimes you find out, sometimes you don't. Don't try to make errors. They just happen. Lovely Condor, Mystery Orcs, Friendly Cow, Crow, and Winged Jedi, Remarkable Dragonfly. Good to see you there. When doing a 2-sample t-test, the variables will be what? We got this. Big review question here. Big review one. Big review. This could be like testing the age of UT students versus their level in class, whether they're graduate or undergraduate. It could be how much money do students spend on or off campus. So spending money and on or off campus. It could be how fast do you run a mile and are you an athlete or not an athlete? Need the graphic put up earlier, Working Bird? Let me know. I'll send it to you. So if you notice, athlete, not athlete is categorical, and money you spend or how fast you run is quantitative. So one is categorical, one is quantitative. If both variables are quantitative, what are we doing? This is a misconception. I know you're thinking T quantitative, but if both are quantitative, what are we doing? If both are quantitative, we're not doing a t-test. If both are quantitative, we're doing QQ straight enough, no outliers, plot doesn't thicken, or just QQ straight enough, no outliers. What are we doing? We're doing regression. Chi-squared is when both are what? And John, good work. Chi-squared is when both are what? So this is regression. Here, we'll write it on here. Let's do a quick review slide of this. So both categorical leads to this, which is chi-square. This is just a no. We don't use identifiers. Just if you see identifiers, no. Both quantitative leads to scatter plots, and this would be correlation or regression. And categorical quantitative is going to be for our class, t-test, 2-sample. Josh Mueller, GE, chat, mention everybody. And leads to side-by-side box plots. And technically, it could do logistic regression, but we're not doing that in our class. So this is going to be the 2-sample t-test. Does this make sense to everybody? Quantitative is 2 quantitative variables, like height and weight, which is regression fitting the line. And this would be something like on or off campus, and then like money spent or something like that. And we don't use identifiers. No. Identifiers are for identifying. Okay. Lovely Condor in the lead. When working with statistical power, which of the following do we have the most control over? Statistical power is the ability to correctly reject the false null. It is controlled by 3 separate things. The 3 things that control statistical power are: how much of a sample do you take? If you take a larger sample, you have higher statistical power. If you have a bigger effect size, which means, like, let's say we are trying to test how good of a basketball player Brian is compared to Darren. Effect size would be the true difference between us. If Brian and Darren are like this, basically the same, that's hard to detect and very low power, the ability to reject the false null. If we're very different, where Darren's way better, that's easier to detect, easier to reject the false null, because we're not the same, the null is false, and thus we have higher statistical power. Alpha is the type 1 error rate, and the more willing we are to make a type 1 error, the less we have type 2 error, and power is 1 minus beta. So you might have heard which of those is the most easy to control, but let's make our quick infographic right here that we've made for statistical power. What are the 3 things that impact power? Does anyone remember? So power, which we do want usually to be higher. Can you repeat the 3 things that impact power? Power is the formula 1 minus beta. kind of winged it on this. Let's see. I hope you got it, Jude. So beta is type 2 error. That's what beta is. Power is the complement of it. And alpha, which is type 1 error. So who sees it? Which of these is going to be effect size is the difference, and then sample size. Which of these is the most easy to control over here? Just take a larger what? Sample size. Alpha 2, I guess. Yeah, I forgot to put alpha on there. But yeah, like you could change your alpha, but why would you not change alpha? Why would you not? You can. It's easy to control. Why would you not change alpha? Why would you not change alpha? Who can give a reasoning? Why would you not just increase your alpha to make your test more powerful? Why would you not just increase your alpha? Sample size is probably the best one, but that can cost money, so sometimes that's problematic. More false positives, exactly. Increasing alpha increases false positives, so you'll have more type 1 errors because you might have, if you increase your alpha equals 10% or 0.10, now you have 10% type 1 errors when you run your test. So yeah, that's got it. Good stuff. Here we go with our last 2 questions, I believe. Calculate the degrees of freedom, freshman, sophomore, junior, senior, and owning a bunny. Now, I wish I'd gone in, and I got to put our little guy in here, our little girl. Look at that little girl. There's the little girl. That's Celeste, named after the mountain. There's Celeste on there. Freshmen, and owning a bunny is a great joy in life. There's Celeste. He's even got eyeshadow. Beta is type 2. That is correct. Alpha is defined as type 1. So whatever your alpha is your type 1 error rate. And then Celestial Bunny. She's the Celestial Bunny. This is so cute. She's so cute. You just pet their little head. You just go. That's when you pet a bunny. You pet their head. Does anyone know why you don't pet the backside of a bunny? Does anyone know? Bunnies are prey animals. They don't like that. Beta is type 2. It's just how we define it. It's like a bunny, beta being type 2 error and alpha being type 1 error. It's just the way we make it work. So we define in statistics, alpha is called the type 1 error rate, which is your level of significance for the test. And beta is the type 2 error rate, which is calculated from N, effect size, and also alpha. So the 3 things that impact, I wish I saw that graphic up. So the 3 things that impact beta are going to be sample size, effect size, and alpha. They're inversely related to beta, as in if you have a larger sample size, you have a lower type 2 error rate. If you have a bigger effect size, you have a lower type 2 error rate. If you have a bigger alpha, you have a lower type 2 error rate. If you have a lower type 2 error rate, which all of these make lower by being higher, you have a higher power of the test. We have a bunny room. And for this question, everyone basically got a yes. Because, Brian, this is a what by what. What is this? So a lot of people know how to do this. This is rows minus 1 times columns minus 1. So, Brian, this is a what by what. What is this? What is this? It's a 4 by 2. And you just delete one finger. 3 times 1. Once you know how to do these, you got it. Yeah, we have a really good bunny room. So we have 2 bunnies, Ricky, Bobby, and Celeste. We had Morty and Jolly, and I miss them dearly. Jolly had a liver lobe contortion, and Morty got cancer. But they lived good lives. And then we spent some time bunnyless, and now we have Ricky, Bobby, and Celeste. And all of our bunnies are adopted bunnies. They've all needed homes, so we found them homes with us. And they're very, very happy. So we're trying to bond the bunnies. Ricky Bobby is 3rd, but he's 1st now. Oh, it's all right. They will live honest. That's one. Yeah, we do have. And then, oh, do I have a picture of Jolly on here? I'll have a picture of Jolly too. No. Okay, I got to show a picture of Jolly here as we finish off. There's Celeste. Jolly was our little guy. There's Jolly. So that's actually him in the kitchen. He's such a little guy. He was so cute. And so, yeah. He's a little guy. And Morty's on the Discord. Morty's in the syllabus. They are our little ones. This is actually from, was it Halloween? There's Morty right there. That's Morty. So, yeah. He was my favorite. Sorry to have favorites, but he was. Because I could snap, and he'd run to me. I missed that. I'd walk in the room. I'd open his cage and I'd go like this, and I wouldn't even give him food. I'd just give him head pets, and he'd bury his head down against me. He would just press against me and just let me pet his head, and then he would like, if I like went away, he'd like, and I'm like, come on, I petted you for 10 minutes, like, come on, little guy. But he was he's a good guy. So, last question: how could someone make this test more powerful? Hopefully, you listened in here. Bunnies make noises. They do. They can chirp if they're super duper happy, and they can grunt a lot of times if they want attention or food. They can also thump when they're in danger or fear or annoyed, and they can flop on the ground when they're happy. They can bink when they're happy. Yeah, it's very interesting. Bunnies make noises. They can make noises like verbally, and they can make noises expressionally. Remember, the 3 things that impact power are going to be sample size, effect size, and alpha. Now, effect size is not something we really change. Effect size is just the true difference. So when you think about, like, you go and you're sick, and they're like, are you really sick? And you're like, I have a little cough. I don't know if I'm sick. That's a small effect. But if they wheel you in and you're passed out, that's a big effect, and pretty easy to notice that someone's sick when there's a big effect. Because the null will be that you're healthy, and the further you are away from the null, the bigger the effect is, and the easier it is to detect and reject the null that you're healthy, hence a more powerful test. With this also, how could someone make this test more powerful? The answer is pretty obvious. It kind of relates to the other ones. You could, well, think about this. If you decrease alpha, alpha would decrease the type 1 error rate. Type 1 errors are false positives, which would mean you're less likely to reject the null. You can't really increase 1 minus beta, which is power, and you can't really change the effect size. The most common way to make a test more powerful is to get a bigger sample, which means you're better able to find results if results exist. So, well, that's got it. I think that's everything. Might have another picture of Morty in here. We have so many pictures of our bunnies. That's a Morty video. Get another Morty picture. So big. He's the best. Oh, this is the best. We caught him passed out under the table. We'll look at the winner here, and we'll go to McLovin Island one last time. But that's Morty passed out under the table. We're just like, we look over and we're like, don't say anything. He's just passed out. It's just passed out. But there he is. Big zoom in on Morty passed out right there. Just totally asleep under the table. And then he was in his little car. He's on the syllabus in his little car. But he's such a good job. Let's go to McLovin Island. Here we go. Eat me, boy. Top 3 winners, please email me for your $20 Amazon or Starbucks gift card. We have Friendly Crow. Wow, you came back into 3rd. Nice job. Mystery Orcs, amazing work with the funny glasses. And last but not least, we have Lovely Condor. And I want to say a big thank you. I think I got really hungry during the Kahoot right here. We had some lunch, but I probably didn't eat enough. I'm going to go home. I'm going to relax. I'm going to respond to some Discord. McLovin Island will not be forgotten. Got 2nd. Let's go. Nice job right there, Jude. 1st podium. Well, make sure to email me, Starbucks or Amazon. Let me know in the email to say, Brian, I won. Send it to this email, the one you have probably, and pick Starbucks or Amazon and email me. I'll be back home in a little bit. I'll be replying. I'll be eating some dinner/lunch, whatever we eat at this time of the day. Need to see cat named Quant. Let's go do that. We got a working bird. I got to find it. Let's see if I can find it. Okay, we're going to set this up. I haven't done this forever. Let me see if I do have it. That's going to be a fun ending. Okay, where is it? I know the program I need. Okay, here we go. I think I found it. Let's see if I can do it. You're gonna be like, what in the world is going on? It's loading up. Let me see if I have the device I need in here. Oh, I think I have to go to my drawers. Yeah, okay, do I have this? One sec. I still have Kahoot t-shirts. I need to give these out. Kahoot sent them. I still have Kahoot t-shirts. Mediums. Still have Kahoot t-shirts. Let me see if I can... It's not there what I'm looking for. Impromptu. Yeah, if you swing by my office, I can get you a Kahoot t-shirt. You guys can probably still hear me right now. Where is the device? Why would I hide this from myself? Must find device. Okay, if we don't find it, we're gonna give ourselves another moment here. I can try without the thing I need. Oh man. Looking for the webcam. That's insanity. Midnight snack and dinner. Where is it? Where did I put it? Supposed to have. Where is it? I don't see it. Let's see what happens if I try this without it. All right. Yeah. Okay. It's loading up. That's not it. All right. It says that that's it. No. Give me a second. Gosh, it was 2023 we did this. Oh, I'll go check T Invoice right after this. Really? Let me go to the 2023 version of this, and I'll see if I can get it. I'm gonna be really sad if we lost this. Okay. Margaret does not play about her bonus. True. Okay, let me go look at the T Invoice right now too. Open project. Dang it. That's not the right thing. I'll wonder if this will work. You ready? We're gonna try something right here. Okay, so here we go. We're gonna try this. We're gonna see if this works. I gotta find it. And the T Invoice is still at 69. They don't update it a lot. We're so close to making this work. Why can't I find it? You're gonna be like, what in the heck? It's not this. That's not it. Nope. Ah, that's not right though. Where is it? Very worth it. I hope this is. I could set it up again right now, but okay, give me a second. Well, I'll show you what it is because I don't know if I can get it working right away. So what it is they have this thing, character creator, and we made something called a cat named Quant, and I can't find our thing. I still have it called right here, a cat named Quant. So there's a cat named Quant, and I made this character called, I drew it in class, and we called it a cat named Quant, and then we made it, and so let me look again for it. And then I made it appear in class, a cat named Quant. Oh, wait a minute. Might have found it. Open. I'll show you a cat named Quant, because I think I found the picture of it. Okay, so let me open this. Photoshop. I drew this in class, and then it became a thing. And then I got the character creator working and made it. I animate. There it is. Yeah, there's Deadpool. So where'd cat named Quant go? Cat named Quant. So I made this right here, and then I had it speaking to students in class, and I had it appear, and I put it into character creator and animated it, and it was like a horror show. So because I drew this, I don't know why I even drew it. I drew it for some weird reason, and then it like appeared in class. I was like, "Hey guys, I got a special guest," and it was like, it was like, "Hi students," it was like, "How are you doing?" And its mouth would move like this, and so we called it a cat named Quant. And then its eye moved too. Like I got its eye to move, so it's like I would just like googly eye around, and it was just like because I added its jaw, so its jaw had to have a hinge on it, so that way its jaw could like flap up and down. And we just did that one semester. Like that was because someone just said a cat named Quant, and then I drew it, and I was like, here, I'll draw a cat named Quant, and they're like, that is horror, like horror fuel, and long right there. The bloodshot eyes are doing it. I know, right? So it was like. It just became this thing. I could find the video of it, but it was, I don't know why I can't find it in character creator. Let me try like a few more of these files or whatever, but open project number 4. Let's see what this is. Is it gonna open? I mean, it looks like it's it when you go to it. Hello. Random scene. I think I also did one for myself. Like I made a me. I'm like missing all my stuff. Character animator. I don't know why. Looks like Abby. I have no idea why this. So it's around October 31st. Maybe, okay, give me 1 second. We're going to go find that video from class, and I'll show you it. We'll end with that. Let me turn off the Kahoot music. Thank you, everyone, for just chilling for a moment. Having a nice moment, relaxing right here. We have officially finished the review for now, and I'm going to go find the details. I need a nap, too. It'll be in this video. I'm going to go find the video. I have to go find the class real quick. YouTube Studio. So content probably needs some. Yeah, second breakfast would be good. I'm gonna go home and get some second breakfast. Okay, live stream, and we gotta go way back. I've done over 2,000 live streams. 2,173 live streams. Crazy, right? Crazy live streams. I have second breakfast, partially lunch now. My wife made homemade granola bars. They are amazing. She is amazing. I am very, very lucky. Here we go. So here's the stats class here. Let me block it out. And here's a stat class here reviewing. Chapter 19 reviewing. Okay. Oh, is this the one where I broke? There was one where like the thing froze the whole class. It is. Oh my gosh. This So this class. Oh, I think this is the next one is a cat named Quant. So what happened was I was frozen this whole class, and like I just was frozen, so we took my face, and all I did was I was just appearing on the screen. Like it was just me appearing randomly on the screen, and that's what we did because I was frozen. Something happened with the camera, and then we even like duplicated me across the screen, and I was just talking the whole time, and I was like, okay, I'm not here, so I can't. Maybe it was something I did with the other thing, but I was like, well, whatever. And the class was cracking up. Matt Pat. Oh yeah, and Matt Pat. With Matt Pat, he did whatchamacallit? Game Theory. That Matt Pat? I don't know him, but I know of him. Oh, here it is. We gotta turn up the volume. Maybe you'll be disappointed. Okay, let's turn up the volume here. Oh, Five Nights at Freddy's kids? Yeah. That was after my time, but here we go.
It's me. I'm a cat named Quant. How you doing, Lita? How you doing, Alexis? How you doing, Kate? It's me. Brian drew me last class, and now I've come alive. I'm a cat named Quant. Ah. What's up, Emma? What's up, Rachel? What's up, Ashley? Cat named Quant out.
Oh my. That's the kind of I try to make each semester, like I said, I want to make each semester like we have our own jokes, we have our own things. And this is before I found out I had a hip problem, and I was standing there. Look at me standing before like Brown's got hip problems. Oh man! And then you found out you had a hip problem, Brian. So now you sit. Why you got a standing desk? Yeah. So that was a cat named Quant. That was the fun we do. I think I got the idea eventually Google. Yeah. I have hip impingement, and they told me that. They're like, you could get a hip replacement. And I was like, let's not do that. Let's do physical therapy. Well, with that, I'm gonna head off here. I'm gonna get some food. Everyone get some third breakfast. Enjoy yourselves. Thank you so much. We'll be back. We'll be doing more streams. Until then, bye for now, everyone. Bye.